be the host for this defense. I would like to welcome you all to Awais Salman's PhD defense. The main supervisor for Awais has been Professor Jinyu Yan. I will especially welcome the faculty examiner, Associate Professor Mika Järvinen from Aalto University.
Thank you, and good morning, everyone.
And then we have the examining committee. We have Professor Jukka Kontinen from Tampere University.
Thank you. Good morning, everybody.
And then we have Associate Professor Elisabeth Wetterlund from Luleå University of Technology.
Good morning.
And then we have Associate Professor Cecilia Sundberg from the Swedish University of Agriculture Sciences.
Good morning.
And we also have with us the reserve Associate Professor Xinqing Zhang from Dalarna University.
Thanks. Good morning, everyone.
Yeah, welcome. So just briefly about the procedure. I have hereby then opened the public defense as a chair. I will then leave the word to Awais for presentation of his work. After that, Mika and Awais will discuss the work in an opposition. And then only those, though they will have the possibility to talk and discuss the work. After that, the examining committee will have the possibility to ask questions to Awais. And then when they are satisfied with their questions, all of you, both online and here in the room, has the possibility to ask questions to Awais. After that, I will close the public defense part. The examining committee will have a meeting to make a decision. And after that, we will come back here, both to this Zoom room and to this physical room, and make the announcement of the decision of the examining committee. So that's the procedure. So by that, I would like to give the word to Awais.
Thank you, Eva. Welcome and thank you for coming to my thesis defense presentation. I am Awais Salman, and today I will present my work entitled Waste Integrated Biorefineries, A Path Towards Efficient Utilization of Waste. There will be three main agenda points in my presentation today. I will start with the motivation behind my work, aim of the thesis, and the research questions. Major portion of the presentation will be occupied by second point, where I will present the proposed solutions to all the research questions. And I will finish with some of my contributions, conclusions, and future work. In 2019, approximately 2.1 billions of tons of waste were generated globally. And on your right-hand side, you can see how it was treated. Approximately 70% of waste was either landfilled or dumped in open. Only 13% of waste was recycled and 11% was incinerated for energy or just for the reduction of waste. And generation of waste is expected to increase to 3.4 billions of tons by 2050. So instead of landfilling and dumping, we need to recycle more of our waste. And as for the non-recyclable organic content of energy, organic content of waste, it should be converted into energy. But here comes the catch-22. Sweden is already recycling approximately 35 to 40% of its waste and converting more than half of its waste into energy. And which is exactly the hypothesis behind my work. That the current waste management system in Sweden, though state-of-the-art, very efficient, still has a lot of potential and room for improvement. And the main aim of my thesis is to increase the product portfolio of existing waste management technologies through integration of new thermochemical processes. Before integration of thermochemical processes, let's have a brief introduction about the existing waste to energy industries in Sweden. On your left-hand side, you can see the biodegradable fraction of waste in Sweden, which is converted to biomethane through anaerobic digestion. Lignocellulosic waste can also be converted partially to biomethane, but most of it is non-biodegradable and has to be transferred to other facilities, for example, combustion alongside refuse-derived fuel, or simply RDF. In Sweden, RDF is converted to heat and power via combustion in combined heat and power plants mainly. And the last fraction of waste that was considered in this thesis is sludge collected from wastewater treatment plants, which can also be converted to biomethane through anaerobic digestion. But anaerobic digestion also produces a byproduct digestate, and digestate is produced from the food waste, can be utilized as fertilizer directly, as it is currently happening in Sweden, but not if it is produced from sludge, as it contains heavy metals and contaminants, which require some kind of a post-processing before its final application. Combined heat and power plants has their own limitations. Variation in district heating demand throughout the year is the biggest of which affects the performance of CHP plants, and plants has to operate at partial load for more than half of the year with lower efficiencies. Uncertainty in electricity prices and growing share of renewables for electricity will also affect the future performance of combined heat and power plants. What are the other thermochemical processes other than combustion that we wish to integrate with existing waste to energy industries? In this thesis, I considered gasification and pyrolysis. The main difference among these processes is the amount of oxygen they utilize. Combustion takes place with excess oxygen, while gasification in controlled oxygen environment, and pyrolysis in the absence of oxygen. Combustion produces hot gases, heat from which can be recovered in the form of steam, electricity, or district heating. Waste and biomass can be gasified to produce synthetic gas, which can be upgraded to liquid and gaseous biofuels. And pyrolysis produces liquid bio-oil, solid biochar, and syngas. Bio-oil can also be upgraded to biofuels. So these processes are present that can treat waste. Why not implement them on standalone basis altogether? Why there is a need to integrate these standalone gasification and pyrolysis with existing waste to energy industries? I will try to explain this via the simple chart. On the horizontal axis, you can see the technology status of various thermochemical process technologies from research and development towards maturity stage. And on the vertical axis, you can see their anticipated cost for full-scale application. As expected, incineration of municipal solid waste, CHP plants, and anaerobic digestion are commercially mature technologies with lower capital expenses. And gasification and pyrolysis are still lying around demonstration and deployment phase with higher expected capital cost. Here comes the biorefineries, although they are still at R&D phase, but their expected cost is expected to be lower as compared to standalone gasification and pyrolysis process. So what are biorefineries? It is sustainable processing of biomass or different fractions of biomass into spectrum of marketable products, which can be biochemicals, biomaterials, biofuels, or simply power or heat. In this thesis, I integrated existing waste-based combined heat and power plants and anaerobic digestion process with gasification and pyrolysis and converted them into waste-integrated biorefineries. To achieve the aim of the thesis, which is to increase the product portfolio of existing waste technologies through thermochemical process integration, 4 different research questions were formulated. First research question deals with the integration of gasification and pyrolysis with combined heat and power plants, and the limitations and opportunities for which were determined and reported. Second research questions, the integrated processes were extended to produce different biofuels and the feasibility of current waste-based CHP plants, shifting from cogeneration to polygeneration of biofuels, heat, and power were evaluated. And third research question deals with the integration of thermochemical processes with existing biogas plants. Instead of incineration, lignocellulosic waste was pyrolyzed, and its products were used to enhance the biomethane production through integration with anaerobic digestion process. and digestate from the and digestate collected from the anaerobic digestion of sludge was processed thermochemically to recover energy and nutrients. 5 different case studies were designed, developed, and evaluated to answer the first 3 research questions. As for the 4th and final research question, let's leave it for the time being. I will come back to it later after answering the first 3 research questions. 8 publications on which the thesis is based are shown here. 2 of them are conference articles and rest are journal publications. Now I will present the proposed solutions to all the research questions that I just described. I will start with a brief description of the methodology that was used for the evaluation of design of these waste integrated biorefineries. Existing waste to energy industries were integrated with new thermochemical processes as per engineering principles. Different cases and scenarios were designed and developed to fully evaluate each integrated option. Different modeling and simulation tools were used for the evaluation of waste integrated biorefineries. For example, Epsilon Professional, a flowsheet-based software, was used for the modeling and simulation of the part load behavior of CHP plants. Aspen Plus, another flowsheet-based software, was used for the modeling and simulation of different thermochemical processes. For example, combustion, pyrolysis, gasification. In some cases, programming language, for example, Python, was employed for the modeling of lignocellulosic waste pyrolysis. For the economic analysis of the integrated processes, discounted cash flow method were used. Different performance indicators were employed in different papers. The main one is some of the main technical and economic performance indicators are here. As the new processes are integrated with the existing one, so the annual production potential of the new integrated thermochemical process is reported as the main performance indicator. And so is the change in efficiency in the new process as compared to the standalone one. In some of the cases, flexibility of the whole system is also reported as a performance indicator. As for the economic performance indicators, they are reported in terms of net annual profit, capital expenses, net present value, payback period, and rate of return. In this presentation, I will only present the economic results in terms of net present value. First research question is answered in 2 parts. First part deals with the thermochemical processing side of the integration with CHP plant. An existing CHP plant located in Västerås, Sweden was used as a basis for retrofitting of thermochemical processes. The plant combusts RDF in the presence of air. Heat from the hot flow gases can be recovered in the form of high pressure steam, which is then expanded in a turbine to produce 50 megawatt of electricity when plant operates at full load. Saturated steam leaving the turbine is condensed to produce 100 megawatt of district heating when plant operates at full load. And flue gases can also be condensed in a flue gas condenser in the reference CHP plant to provide an additional of 30 megawatt heat approximately. For the case 1, 3 different gasifiers and a pyrolyzer was integrated with reference CHP plant. I will only explain one gasifier and a pyrolyzer in this presentation. But first, waste has to be dried from 40% initial moisture to the 10% final moisture. And steam was used as a drying media, which was exported from the CHP plant. Dried feed is then entered into the gasifier, which is dual fluidized bed gasifier, and steam was used as an oxidizing agent that was exported from the CHP plant. But it is a dual bed gasifier, so there must be a second reactor, and the boiler of existing CHP plant acted as the second reactor, which combusts the biochar from the gasifier and returns the hot sand to provide the heat indirectly to the gasifier. Syngas leaving the gasifier contains small amount of tar, which needs to be reformed for further downstream processing, and steam was used as a reforming agent, which was once again exported from the CHP plant. Syngas leaving the reformer was cooled and entered into the water gas shift reactor, where hydrogen to carbon monoxide ratio was maintained for further biofuel processing, and steam was used to shift the carbon monoxide towards hydrogen that was once again exported from the CHP plant. Heat from the syngas cooling was also recovered in the form of high pressure, in the form of inlet conditions of steam turbine, which was sent back to the boiler. The second option, a pyrolyzer was integrated with this reference CHP plant. Biochar and syngas from the pyrolyzer were sent back to the boiler, and bio oil was collected as the final product. The gasifier integrated with CHP plant and pyrolyzer integrated with CHP plant were modeled in Aspen Plus, and they were simulated for under 3 different operational scenarios for whole year. On your lower left-hand side, you can see the actual district heating and power output from the reference CHP plant for whole year. The blue portion shows the electricity curve, and the green portion shows the district heating output. In first scenario, CHP plant was operated at full load, and a flexible size gasifier and pyrolyzer utilized the excess heat from CHP plant, but it was ensured that there should not be any disturbance from the heat and power from the actual reference scenario, and biofuels were given least priority. The second scenario, once again, CHP plant was operated at full load, and a flexible size gasifier or pyrolyzer utilized the excess heat. But in this scenario, biofuels were given priority over power, and power was considered as secondary output. And in the third scenario, instead of a flexible size integration, a 40 megawatt fixed size gasifier and pyrolyzer was integrated. Once again, biofuels were given priority over power, and power was considered as secondary output. The results for the integration of gasifier with CHP plant are shown here. The results are shown here as heat, power, and syngas in terms of megawatt for whole year from January till December for all scenarios. All the vertical scales are kept same for better comparison. Let's remove the heat and power and only see the syngas. As evident, highest amount of syngas is produced in scenario 2, where biofuels were given priority over power, and power was considered as secondary output, as compared to in scenario 1, where power was given priority. Another important point to consider in the graph of scenario 1 and 2 is that in the months from November till February, when CHP plant operated at full load to provide the district heating in winter months, very little or no amount of syngas was produced from the flexible size gasifier. In third scenario, where 40 megawatt gasifier was retrofitted with CHP plant, and the gasifier is able to operate at full capacity for almost 10 months of the year, which is a good sign, but then the amount of syngas is lower as compared to scenario 1 and 2. And I give you the average megawatt in all 3 scenarios to give you a better idea how much they differ in each scenarios. Now the energy efficiency of the retrofitted process is also different in all 3 scenarios. And the highest efficiency was obtained in scenario 2, where electricity was not prioritized and biofuels were considered as a main product alongside district heating. Results show a similar trend when pyrolyzer was integrated with CHP plant under all 3 scenarios. But the amount of bio-oil as megawatt is lowered as compared to the amount of syngas that was obtained from the gasifier integration with CHP plant. And the efficiency of a pyrolyzer CHP-based system is also low. Second part of first research question deals with the CHP side of the integration. And it was determined how they will operate when they will be retrofitted under energy-intensive gasification and pyrolysis process. On your lower right-hand side, you can see the actual district heating output from the reference CHP plant, and approximately 504 gigawatt hour of district heating was produced for a whole year to the community. Now, the heat can be extracted from CHP plant by a number of points. For example, gasification requires steam. It can be extracted as high pressure steam from the boiler, or it can be extracted as low pressure steam within the turbine. But pyrolysis occurs in the absence of oxygen. So it cannot utilize steam directly. So heat for pyrolysis can be extracted through flue gases in the boiler. Now, simulations were performed while CHP plant was operated at full load, and excess heat was extracted from these points for integration, but it was make sure in all the simulations that there should not be any disturbance from the district heating output according to this curve. Simulation shows that it is possible to extract approximately 315 gigawatt hour of heat annually for the integration of gasification process through high pressure steam. And it is also possible to follow the district heating curve as per reference scenario. But when heat was extracted through low pressure steam, the amount of heat available for integration is lowered to 260 gigawatt hour annually, and also the amount of district heating produced is lower to the reference scenario. As for the heat extraction from the flow gases, it was almost similar to the heat extraction scenario where high pressure steam was extracted, and it was also possible to follow the district heating output curve as per reference. The opportunities and limitations for the integration of thermochemical process with CHP plant were determined. The integrated processes were extended for the production of different biofuels and their feasibility were assessed. 4 different biofuels was considered in this thesis. Biomethane, methanol, and dimethyl ether are first 3 of them. And drop-in biofuels are the 4th one. Drop-in biofuels are biofuels having similar properties to gasoline and diesel, and they can be produced via a number of methods. For example, conversion of syngas from gasification to Fischer-Tropsch fuels and upgradation of Fischer-Tropsch to drop-in biofuels. They can be also be produced via upgradation of ethanol to gasoline via MTG process or through upgradation of bio-oil that was produced from pyrolysis process. Quite a lot of results were obtained for the production of biofuels annually in different scenarios. But in this presentation slide, I will only present the maximum annual production of each biofuel that was produced through thermochemical process integration with reference CHP plant. The graph for biomethane, methanol, and dimethyl ether are shown differently on your left-hand side to the graph for drop-in biofuels because data was different for both base cases. As I mentioned repeatedly in previous slides, that we did not disturb the district heating in any of the simulation scenarios. So let's remove district heating from the equation. And highest amount of biofuels was produced for in the case of biomethane and methanol as compared to dimethyl ether and drop-in biofuels. And if you see the drop-in biofuels, they are produced in higher quantity when they were produced via pyrolysis as compared to when they were produced via gasification. Now, electricity production also gets affected through integration from CHP plant. And reduction in electricity was higher when biomethane was produced through CHP gasification-based system as compared to methanol and dimethyl ether. And there was no reduction in electricity when drop-in biofuels were produced through thermochemical process integration. Efficiency is another important key performance indicator that can give us an idea about the feasibility of chemical processes. And highest efficiency was obtained when biomethane was produced as compared to methanol, dimethyl ether, and drop-in biofuels. And drop-in biofuels were produced with very low efficiency. And if you remove district heating from the drop-in biofuels system, the efficiency will lower to 30 to 35%. And the last performance indicator that I want to show you for all these biofuels is economic one, net present value in terms of euro per megawatt hour. A basic rule of thumb is that higher the net present value, better the economic performance of the project. And once again, biomethane shows higher net present value as compared to other biofuels, but in economic results, drop-in biofuels shows better economic performance, slightly better economic performance than methanol and dimethyl ether, probably because of higher prices of drop-in biofuels. The research question is answered in 2 parts. The first part deals with the integration of pyrolysis with anaerobic digestion process. A reference biogas plant located in Westeros was used as a basis for integration. The plant utilizes approximately 23,000 tons annually of biodegradable waste collected from our kitchens and restaurants and produced approximately 15 gigawatt hour of methane at a 52% standalone anaerobic digestion efficiency. Lignocellulosic waste, if combusted, it produces heat and power at an efficiency of 67%. But instead of combustion, lignocellulosic waste was pyrolyzed and its vapors were upgraded to biomethane. And biochar obtained from the pyrolysis of lignocellulosic waste was added into the anaerobic digester where it acted as an adsorbent to enhance the biomethane production. Modeling and simulation results shows that increase in biomethane production is from 15 gigawatt hour annually to 40 gigawatt hour annually in the integrated process. And the efficiency of the integrated process is also higher. As for the net present value for the integrated pyrolysis and anaerobic digestion process, it is also higher and approximately 325 euros per megawatt hour of net present value was obtained, which is higher than any of the net present value that we get in the previous slide for the thermochemical process integration with CHP plant. Now, anaerobic digestion also produces a digestate. And digestate, if produced from biodegradable waste, can be utilized as fertilizer directly, but not if it is produced from sludge, as it contains heavy metal and contaminants, and which requires some kind of a post-processing before its final application. Second part of third research question deals with exactly this issue. A reference wastewater plant located in Eskilstuna, Sweden was used as a base for this integration. Digestate was dewatered into liquid and solid digestate. Nitrogen was recovered from liquid digestate, and solid digestate still has a lot of moisture, which was dried before thermochemical processing options. 3 different options were modeled: combustion, pyrolysis, and gasification. And whole system was analyzed, whether it is capable of producing enough heat for nitrogen recovery, also enough heat for drying, and also to provide if there is any excess heat left, if any. Spoiler alert, no. The annual production of digestate from the reference plant was 64,000 megawatt hour annually. And simulation shows that drying and nitrogen recovery requires significant amount of energy. In fact, so significant that the total heat required is higher than the amount of digestate that we wish to process. And when we will process this digestate, the output is even lower. So none of the process is feasible on standalone basis. How can we make the process feasible? Drying is the bottleneck step here, which requires a significant amount of energy, which can be integrated via any existing waste to energy industries. Let's go back to the CHP plant from the case 1 and 2. Turns out there is a fourth point where we can extract the low temperature heat for the drying of digestate. Flue gases are leaving the boiler at 163 degrees centigrade. They enter the flue gas quench and flue gas condenser respectively to provide additional district heating. Sludge drying was integrated before the flue gas quench. Quite a lot of results were obtained, but let's only see the one result. Maximum amount of sludge that can be dried to 40% integration, 40% via integration with CHP plant was equivalent to 5,000 kilogram per hour. But the integration of sludge drying will also affect the district heating from the flue gas condenser. And simulation shows that there is approximately 1 megawatt reduction in district heating from the flue gas condenser, which does not look so much higher, but it actually is quite high. So what else we can do? So we gave CHP plant an offer, they can't refuse. So dried sludge was sent back to the boiler and co-incinerated alongside with biomass. Simulation shows that approximately 6 megawatt of biomass savings can be achieved if we co-incinerate the sludge in the boiler. So at the end, it is a win-win situation on both sides. Now for the fourth and final research question. Which deals with the uncertainty analysis of the early stage waste to biofuel processes. And why there is a need to study the uncertainty analysis, I will try to give few examples. My analysis or my thesis, I used methanol price a couple of years ago as 64 euros per megawatt hour. But I checked prices a couple of days ago, which has been reduced to 45 euros per megawatt hour. And reduction in drop in biofuels was from 180 euros per megawatt hour to 150 euros per megawatt hour in current prices. The heating value for RDF was used from the CHP plant and equivalent to 12 megajoules per kilogram. But I have seen some articles where they are using as high as 18 megajoules per kilogram of heating value, probably because of higher plastic content. So waste is heterogeneous. Its properties varies in different regions, in different seasons. And so are the operating parameters of thermochemical processes. And literature is filled with different set of capital investment for the same equipments of thermochemical processes. And waste and biofuel cost will also affect in future with uncertain market conditions. For fourth research question, Monte Carlo simulations were performed by considering the uncertainties in inputs, and their effect on uncertainty in outputs were determined. Random numbers were generated for the uncertain inputs with certain range, and they were put in hundred of thousands of simulations, and probability of outcomes were determined. I will only show two last graphs. one technical and one economic for this research question. Let's see the technical one about the probability distribution of biofuels in terms of megajoules of biofuel per megajoules of waste in terms of box plot. Biomethane shows higher energy output probability as compared to other biofuels through Monte Carlo simulations under uncertain conditions. Methanol and dimethyl ether can also give higher output in some of the conditions, but they will vary widely with changing conditions. And they also have quite a lot of outliers, and they show higher sensitivity with uncertain input. Drop-in biofuels, though, show less sensitive towards uncertain input conditions, but their energy output probability is lowered as compared to the other biofuels. And the last graph that I want to show you is the probability distribution of all the biofuels produced through thermochemical processing in terms of net present value, million euros. There were so many outliers obtained in the data, so let's remove them first. And let's distinguish the positive and negative net present value. And now please only focus on the middle line in the boxes, which shows the median value, which is positive for all the biofuels, but overall distribution is not, which lies around positive and negative net present value. And once again, biomethane shows better economic performance under uncertain economic conditions as compared to the other biofuels. And biofuels have 50% of values which are negative net present value as compared to the other biofuels. Some of my contributions. The main contribution of this thesis is the provision of waste integrated biorefinery and process integration approach and methods for the modification in existing waste industries in order to make them more flexible in terms of both products and operation. Guidelines were given for different operation scenarios for gasification CHP-based integrated system and pyrolysis CHP-based integrated system. Process models and simulation methodologies were also provided in different articles towards simplification in process retrofitting in existing waste energy industries. New processes were given for the integration of pyrolysis with anaerobic digestion process, and uncertainty analysis guidelines were provided for the future waste to biofuel early stage designs in order to reduce biases in results. Some of the specific conclusions for different research questions. We have seen that effect on CHP performance through pyrolysis integration was lower, but then pyrolysis produced lower energetic return. We have also seen that modification required for CHP plant to integrate pyrolysis is different as compared to the modification required for gasification. As for the biofuels, biomethane show higher efficiency, higher economic return as compared to other biofuels. Dimethyl ether and methanol are interesting alternative biofuels with reasonable efficiencies, where their economic benefits are largely dependent on their prices. As for the integration of pyrolysis with anaerobic digestion, it can increase the biomethane production and also produce it with lower production cost. And digestive sludge, even though it has lower energetic value, but greater benefits can be achieved if it is integrated with CHP plant for its drying. And inclusion of uncertainty in all these early stage designs is very important in order to reduce the biases in the results. Some of the future work in this thesis, I only considered biofuels, but why not biochemicals or bioproducts, or why not integration of recycling of waste with the energy industries? For sludge, I only consider thermochemical processes which occurs at higher temperature and requires drying. Hydrothermal carbonization and liquefaction can be another option for sludge. And production planning and optimization is important also as a next step. And I consider steady state simulations mainly. In some cases, I did the part load performance of CHP plant, but dynamic analysis is also required as a future step. Any take-home message? Although most of you are already at home, but still, I only consider waste here, but waste is a very small part in the bioenergy spectrum. And most of bioenergy is utilized for cooking. Approximately 3 billion of people are using bioenergy as a cooking in developing countries, which occurs at low efficiency, which is hazardous for health, especially for women and kids. and also has a greater environmental effect as compared to the clean options. So we need to design new processes not only for the waste to energy, but also for the whole bioenergy. And with this, I want to thank you, all of you, for listening and coming here. Thank you.
Thank you, Awais. So now we open for the opponent to discuss the work with Awais. Please, Mika.
Okay, thank you. And thank you for the very nice presentation. I think this is, I have been reading and reviewing the thesis for already a couple of weeks. And it's a quite massive thesis, I would say. And it's listening to your presentation, it was really nice, like already many of the questions I had in mind, I think they came very clear in your presentation, since like it's very, in a very compact way. So this was very, I really enjoyed listening to the presentation. Generally, your thesis, the topic is extremely important in the current world. There are many reasons for this. The population of the Earth is continuously increasing, and of course, when more people are, for example, we are eating more, producing bio-waste, but also, for example, the use of plastics are increasing very heavily for packaging use, for example, and then waste issues, they are very important in that sense. So the topic is extremely important. Also in emission-wise, this is a very important topic. The waste is partly fossil still, like concerning the plastic side, but also bio-based. But I will have some more general questions to begin with. But in general, I really think that the thesis is a nice piece of work, and I was very happy to be the opponent, and also to discuss this topic in more detail with you today. Okay, but let's go in bit more detail. So first, I will have a bit more general questions, and I want to hear your opinions of general topics. And then I have quite a numerous small detailed comments I would like to discuss. But let's first discuss on a more general level. So always I like to start the defense by asking, like, how did you started this work? So how did it all start? So how did you get the position to work in Mälardalen University, and what was the status there in this research when you started? So had there been already long time research on this topic, or did you start the topic? So please share these ideas with us. It will be really interesting to hear.
So I was lucky with this, my work, because it is very much related to my previous experiences in my bachelor's in chemical engineering. And then in 2012, I came to Europe for the master's in renewable energy, where I was more fascinated over solar first in the beginning, because solar was very hot, still hot topic now. And I started actually thesis in solar, but then after 1 or 2 weeks, I left and I came back to bioenergy. And I did the thesis on pyrolysis, and there I said, okay, let's continue the work with the pyrolysis thing. And I was at KTH during that time, and I was looking for bioenergy positions, and Sweden has so many universities. Like I'm sure Elizabeth don't know, but I have been sending her emails also during my masters, and her like her colleagues also in Chalmers, also in KTH. And then I sent email to Professor John, and he replied in the midnight, okay, he was working at that time also. And then it all started. In the beginning, I was not into the waste. Like if you see my first paper, I was still reluctant of using the word waste. I wasn't using more biomass, waste biomass, or using biomass with waste. I was still focusing on the biomass thing, on the wood thing. But then in the parallel, I was working with lignocellulosic waste integration with pyrolysis. And then with the sludge thing also came. And then I shifted the focus. Let's leave the biomass for now. I can come back it later. Let's only focus on this small part and continue with the waste. So there are 2 or 3 projects that were continuous. And luckily, I have been at the right place at the right time to work in the right topics. And all of them are combined like okay for me in this thesis.
Okay, good. This is always interesting to hear these stories behind the work. So thank you. Then I just really must to give this comment. So you have 8 appendix papers. They were like actual papers included, two of them conferences, and then you also list, I think, was it six papers relevant to the work. So my question is that how was, and you spent 4 years. So I think this is quite amazing. So I'm thinking that the coffee in Sweden must be a bit stronger than in Finland. But to be more serious. So I think at this point, like I think you did manage very well. But what kind of advice would you give to doctoral students? I think they're hopefully some of them listening. So what kind of advice would you give to doctoral students for their thesis project? What have you learned, main learnings from your work?
And the first thing is, it happened with me, like don't compare yourself with the other person's work. And like I consider myself lucky also. I'm able to work in the field that I have been working with my bachelor's and with master's, and it's not the case for so many students. They change their path and they have to learn new tools. And I was working with Aspen Plus before, so I just mastered it, not mastered it, like I just gain more expertise in the tool. But some people have to learn new tools and it takes 1 year for them to learning. So it's better not to compare your situation with other person. That's the form, like first and foremost thing. And also don't compare to the person who is just graduating. Like when I just started my PhD, I've seen some students, they were having so many papers and I said, okay, I don't belong to research. I will not be able to do this. So these like imposter syndrome, you can say. So just these are the most important things in my.
Yeah, thank you. This is very good advice to in a way work in that way independently. So not compare too much with others and do your best, and then you see how far that can take you. Good, thank you. And also, I was planning to ask what kind of background you had, but you already had been using Aspen earlier. I think this was is also very beneficial for the work. So Aspen is also used a lot in my group here in Aalto University. So normally students that have used the Aspen in their bachelor degree, so then they can really fly already in a master's thesis phase. So this is good. Maybe still one more general question. So in a way, a bit highlight this day. So what if you think what has been the best during this time you have done the thesis, and where have been the biggest challenges in your opinion?
Yeah, the best thing. Best thing is yet to come.
Okay.
There's a diplomatic answer. But still, like I was more prouder of my last paper with uncertainty analysis. Like it was quite independent thing from the projects that I wanted to do, and it took whole year for me to do the simulations. And I spent last summer, not this summer, last summer, to do the simulations again and again. Sometimes the computer was stuck and I had to sit for whole night to see if it's working, all the simulations. And that was, I considered it the good thing that I was working there. And the most challenging thing was in the beginning, where like I was trying to grasp like what PhD is. Like in the first month or 2 months, I did not know about the research so much. So I thought that I have to develop my new models. Like I cannot take the previous modeling approach from articles. But then after that, I discussed with my supervisor. They said, no, okay, modeling approach, like science is because of this. You can take their work and extend it. So it's not like you have to develop everything from the scratch.
Exactly.
So
Yes.
in the beginning, I had this feeling. Okay, no, I have to develop everything from the beginning, and everything should be new. And so that was like understanding how research works was the most challenging thing. Still.
Okay. Yeah, that's interesting to hear. And also, I feel that this is a issue for many other doctoral students as well, that we don't realize that, okay, science is about building on the basis of others' work. So of course, when you use something from somebody else, you just need to refer it, and then it's okay. And your own pieces are just like a bricks on a brick wall that you build. But you made many bricks to the wall of science, so that's that's very good. Okay, but let's then move to a bit more technical topics slowly. So currently, like I think last year, the CO2 emissions globally were around 37 gigatons, or in this range. So what is the contribution of waste to this? How do you see? Is it a significant share or is it minor? Just to CO2 emissions.
Okay, waste is incinerated only partially. Like I said in first slide, it's 11% of waste is incinerated. So share must be not so significant. Like I don't know exactly the numbers, but the major share will be in terms of greenhouse gases, methane from the landfilling, or even if you're dumping it open. So CO2 is still not yet in the higher range, but if we make the process for the conversion of waste into energy, or if we will build the plant for the combustion or gasification, something, they will increase in future for sure. And a lot of countries are building waste-based power plants in developing countries, China or India. So it will increase further.
Yes, exactly. And also, of course, we even though it's very small, the direct share of CO2 emissions, but I think there are like topics such as the landfilling. It's very common, and how plastic is treated currently. It's very bad. So also this is, so that's why even at the moment the waste management is a very important topic, that there are so many other impacts in addition to CO2 emissions. But that was a good comment, that if we increase the utilization of waste, it means that also in the CO2 emissions it will increase. But of course, if the total energy consumption would remain the same, so then it means that the need for fossil fuels would decrease, which would be also good. Any comment on this?
We always say like fossil fuel production will decrease, but when I read the numbers from International Energy Agency or from other reports, it does not look like it. Like they will increase maybe in 40, 50 years, but next 20, 30 years, it is very hard to like decrease this number. And like if you see the, okay, I have one backup slide for this
Okay, good.
presentation. So I have to stop here. This. This one, okay, I forgot to find the value for currency, but this is the share of investment in bioenergy in the last decade.
Yeah.
And it is not so much promising as compared to earlier decade. Maybe in future, governments will invest more money in it, or there will be more research, but we still need to work more. And if you see like the status of gasification and pyrolysis in the last 10 to 15 years for biomass even, not for the waste, it is still lying around in demonstration and deployment stage. There are demonstration plants here and there. There are few in Finland and Sweden also, but still it's not getting to commercialized anytime soon. Maybe it will come in next decade, but for waste, it's a different story altogether again. So it will take time, in my opinion.
Yeah, I agree. And also I have been, especially recently, really following carefully the trends of global total energy consumption, and it really, as you said, it's still showing increase. And also it is very interesting to see what are the trends in CO2 emissions also in the future, because for example, according to IPCC, we have this carbon budget, and the longer we wait, the faster we have to then be in adapting the CO to neutral technologies in use to stay within the budget. And yeah, exactly. But I agree with you that we supposed to act faster, and we are not really seeing this yet. But we have to be optimistic and work. Good. So yeah, in waste management and utilization, what do you see are the biggest challenges at the moment, but also in the future? So what's your opinion on this?
Okay, let me formulate my answer. The main challenges will be different in different regions. Like I am from Pakistan, so I will start from this region. There, the main challenge will be the collection of waste in source separated manner. Like when I have been to Sweden in first week, I was fascinated how they were treating waste and how everyone is acting responsible. Not everyone now after 6 years, but most of them are acting responsible. But in Pakistan, we don't do this. Every like waste is mixture of all the things. And in developing countries, changing habits will take time. And it will take decades for changing habits. Like if you see Sweden, it also takes so much years to make them realize, okay, let's all separate the waste from the very beginning and let's treat it in appropriate processes. And the other main challenge is like our this heterogeneous nature of the waste that I mentioned. Like it affects this, like for biomass, biomass is also heterogeneous, but at least it has similar kind of it will not vary widely as compared to waste. If the waste is coming in different seasons, it will show different behavior. I will give you an example of sludge. I was reading recently, like there was a wastewater plant in Eskilstuna, and there the guy was saying, like a couple of years ago, they were getting the sludge with very different properties. And they checked, okay, because the area had more refugees. So that's why their eating habits were different. So that's why sludge properties differ. So these are very small things, but these will make the life of the actual plant management holders more difficult. And other main challenges in Sweden is the opposition of this waste to energy things. So many people still don't consider waste as renewable, and they were still having an against opinion about Sweden, like why Sweden is utilizing for like 50% of its waste into energy. And because people think that everything can be recyclable, even when you see it is not. And companies are also not recycling plastic, and plastic can also only be recycled 1 or 2 times or 3 times, and then it will degrade in quality and all. So these
Yes.
are the things that like we need to communicate more, both with all the parties, not with the researchers, all with politicians, people, policymakers, etc. So these are some of the challenges, in my opinion.
Yeah, I absolutely agree with that. That this is only not a technical problem at all. So as I have been reviewing your work, there are many good technical ideas, but it's as you said, like the social side and also how people behave and how efficient they sort waste. That's very important. And yeah, but very good. That was good. Then let's see. Okay. So I will take the comments in like I start from the beginning of the thesis, and then so they are a bit jumping on the topic, but don't mind, we just do it like this. So already in the summary, you say that although even though gasification and pyrolysis of waste are not yet commercially major technologies, there are greater benefits in energetic and economic terms on these. So what, with respect to this, what do you think? How far are we on the state that this could be really, for example, replacing waste to energy technologies, and what are preventing at the moment? Is it only an economical issue?
Economic issue is one thing, but there are technical issues also. Like combustion is like, I hope I will not get into trouble by saying this is a straightforward process. Like you just take the waste and just burn it at higher temperature. And flue gases can be utilized for recovering heat. But gasification, they are delicate process. And it requires syngas cleaning. And if you want to produce biofuels, you have to reform tar. You have to like remove tar, and tar produced with wood is already difficult to remove. And if you treat waste via gasification, it will, and we don't know which compounds will come in the form of tar because waste has plastic.
Yeah.
And same thing with pyrolysis. Like I think you noticed in my thesis is that for gasification modeling is fine, but for pyrolysis I have been relying so much on the experimental and literature values because we don't have proper models for the pyrolysis of biomass even, and waste is the next story. And pyrolysis of waste will give the bio oil with hundreds of compounds which will vary differently with different things, and when you will upgrade it, it will behave differently, and there will be what's the word I'm forgetting, a specific upgradation methods for each types of the waste. They should be designed like this. So there are technical issues also, not only the economic issues. Economic issues will come later for sure, but for first there are some technical issues that need to be addressed.
Yes, that's true. And also I have been working most of my career with black liquor combustion. So that's the step in pulp and paper making, and even there the Crafts recovery boilers, they are very robust, in a way similar to waste to energy processes by combustion, and they have done a lot of work on the gasification, and there are a lot of technical issues still, and really like even like mechanical issues of how to design a durable refractory linings for the reactor and things like this. Yeah, okay, that's good. So then forward. Then to the page number 1 of the thesis, you discuss the start by fossil fuels and discuss them, and so, and you say that fossil fuels have been in a way the easy way to build economies fast. So what if you compare fossil fuels and, for example, biomass or waste? So why are fossil fuels so superior with other options? Usually, there are a couple of main things, in my opinion, at least.
First and foremost thing is, if we cut a tree, trees are located at different spaces. If you cut it, it will take years to build. And fossil fuels will also take like millions or billions of years to build, but we have already been very high reserves that we are utilizing. It is a very easy option and easy to transport also in the form of oil, in the form of liquid. And then it is efficient. For example, if you want okay, how can I say this? In all the transport industries, when you are using the fossil fuels in terms of gasoline and petrol, when it was started, there was few other cars also in Europe where they were using wood gasifier at that time. But then it went away. Even there were electricity-based cars by 1890 to 1900s, and they were still fade away with fossil fuels because it was convenient. And we had a lot of them. We have a lot of now still, but at that time we were like more hungry for the new technologies, and everything was growing more faster. And if I hope I won't get into trouble in this, but if I say this, we were transitioning more faster during those 50 years than we are in the last 50 years. So
yeah, I think that that is absolutely true, and also I think also that during you mentioned electric cars then in the past history. So I think there will also, of course, a lot of lobbying for different technologies. So I don't know if we have chosen to not to start working on, for example, internal combustion engine development, but instead focus on electrical vehicles. So maybe we would be further on that, like battery technologies and all. But I think it was a big battle between these technologies in the early, and then there was bigger drivers on the fossil fuel side, and this is why we are where we are today. But this is exactly, and also like if you think about fueling your car, for example, with gasoline, and then you have even a Tesla supercharger, and you can with the gasoline you can fill the tank within like 1 minute, 50 liters, and with if you are charging the battery, it's at least half an hour, and maybe you get 80%, and you with fuel you can run much longer. So the energy density is very high. Also, this is, and also as you said, it's so easy. We just dig a hole in the ground. I'll drill a hole for the oil and also well, maybe I'm not going to answer all of the questions myself, but maybe the one thing I could ask also, like collection, like what is the role of logistics if we consider waste and biomass? Do you have an opinion or thought about this?
okay, logistic with waste and biomass.
Yes,
Okay.
like for example, in comparison with fossil, for example, in comparison with coal, you already touched the issue a bit, but maybe we could discuss a bit more on this.
Like fossil fuels, if liquid or natural gas, we already built a very large infrastructure around the world. It is very easier to transport via ships, via tankers, via pipelines. But biomass is solid, and you have to, and it takes large space. As you say, energy density, it takes large space for the same amount of energy if you transfer it through if you transfer fossil fuels with the same truck, you can say. And it is one of the main problem. And also, like biomass is mainly a regional fuel.
Yes, exactly.
And waste and waste is also like in Sweden. Sweden is exporting waste from the Ireland, like this power plant that I mentioned as a reference. They are importing waste from the Britain, but we don't know in future if they build their own waste-based systems, will they send their waste to us in Sweden or not? So waste and biomass is mainly regional transportation, not the international transportation.
Yeah, I agree. Exactly. So there is like in a way, rule of thumb that 1 ton to transport 1 ton of something, anything 100 kilometers cost 10 euros. So this is a very important thing. As you said, it's regional and local. So often maybe the collection radius could be 20 kilometers, not maybe 50 kilometers, but that's it. And then it's very local, like waste, collection waste, the area is limited, but around big cities, that's a very logical way to do it. Yeah, any comment on this?
Can you repeat your question, please? Like the last line.
Okay, sorry. Yeah. So just like what do you think about this? Like that, for example, if we are collecting wood fuels or waste, so there is a limited area that we can use.
Yes.
And well, this was just like ask your comment if you have anything to add to this topic. So.
Yes, like and for example, as I mentioned earlier, like waste is coming in Westeros from Britain, so it is transported through ships. So we cannot say that it is only regional here in this point. But in future, if they will build these systems their own, it will be becoming more regional. And when you take the biomass from the one place, you need to have a more more policy or like environmental policy, okay, to rebuild all the forest again at the same time. That's the main issue with biomass, but waste is a different thing. You are generating waste, we have to treat the waste, and waste will come just like input and output. But with biomass, input is like input for biomass is coming for one region, but then you have to think about the issues, how to rebuild the same biomass again. And like if we only talk about the wood thing, it is hard to transfer from one country or one internationally. But then again, there are energy crops. Like I don't have any expertise on this, but I think that will be easier to transport than as compared to the this wood or waste in future.
Yeah, and also yes, well, for example, wood it's the energy density as such is quite not that high, but for example, wood pellets is something that is being transported from, for example, to UK. They are transporting wood pellets and then burned in big facilities. But okay, good. Then let's see. Yeah, so actually you already took one question. So in the last slide you don't need to show it, but you discussed the waste first and then the biomass. So in the slide it was just in the corner, small area, and the rest is biomass. And as you said correctly, that's used in the developing countries for cooking, and it's wood and animal dung, and also it's a big health issue for women and the persons cooking in small villages. And this was very good. I was planning to ask that, but you absolutely right that it's mainly like the world's energy comes from roughly 10% primary energy comes from biomass, and that's mostly from the developing countries at the moment. So in the Western countries, bioenergy is still a quite small fraction generally. Any comment on this still you want to make?
I don't have much. The only thing is like in developing countries, we don't have other options for cooking.
Mhm.
In my village also, my mother used to cook mostly with wood and with this kind of stoves. And now we have the natural gas based cylinders, but then we have to refill it by our own selves. Otherwise, it's just this thing. So we don't have any other option. So that can be the reason that why we are using more biomass. Like if like in cities in Pakistan, we have natural gas for cooking from state, and there they are not using biomass for cooking. They're using natural gas. So it's more of a thing if it's available for you.
Yeah, but also this is a good point that you mentioned the gas. I think that I have been involved in a couple of projects that they have studied, for example, in Nepal, the use of biowaste to produce biogas by anaerobic digestion, like in small units. So, for example, in the group of restaurants could have their own AD system and use the biowaste to produce the gas that they use for cooking. So something like this could be developed as an option to make it more sustainable, I think, and also more clean, because the burning of the gas is there's like not so much soot or particle emissions from that. So yes, but very good. Then page number 3. So the introduction part. I really like your approach that in the of course these literature citations are very nice in the beginning, but also here how you summarize with the italic text first, the main things, and then go to the topic. But what is something happening? Can you hear me?
Yes, I.
Okay, good. So you talk about the amount of waste that is developed annually, and 2019 it was 2.1 billion tons, and there's predictions that this could be 3.4 billion tons 2050. And then if you at the moment if we take a look at the number of coal used, it's 8 billion tons annually. So in a way these are on the same magnitude, but still it's a very small fraction of this waste is used. So what are the the fraction of waste to energy is still almost invisible, but we know that there's lots of coal. So what do you think is the biggest, it's maybe not even an opinion you have, but what is the biggest difference of the energy utilization of this coal versus the waste to energy, even though they are on same magnitude in amounts, but there are differences? Could you comment on this?
Yes, like even though the waste is 2.1 billions of tons, but waste is different fractions. Like we have so many recyclable materials, and it contains electronic waste also, which is not organic. We cannot do anything from it in terms of energy. And like if we be realistic and only consider about the non-recyclable organic fraction, so it will be even less than half, because now Sweden is recycling 35%. It can be 50% for proper source separation and proper other appropriate methods. So if we take only 30% of the waste that is non-recyclable organic fraction that can be utilized, so the amount will be 3.4 into 0.3, so it will be 1 billion if we utilize all the waste by 2050. And coal is once again there is only one thing: coal, carbon, hydrogen, oxygen, and you just take the coal and burn it. But waste has so many stakeholders involved from the very beginning to the end use. And then, so this will be the biggest challenge. Even though it's only 30% of non-recyclable waste, it is still very high, but I don't think so it will be utilized in full potential by next 30 years.
Yeah, this is, but it's in a way, on the, in my opinion, it's quite surprising that if you weight the amount, they are almost in the same, and still, so we have a big challenge here. That's for sure. Okay, then on page 4, I will try to move faster. Don't worry. So, so you talk about this anaerobic digestion. So, in your opinion, what are the biggest challenges for this in general? You can also compare municipal solid waste, but also, for example, wastewater treatment plant. That sludge that is coming from there. What are the biggest challenges in your opinion on this?
Okay, if you are only specifically asking about anaerobic digestion, then I don't have proper expertise in the process parameters, like how process is happening. So like my focus was more on the gasification, pyrolysis, and combustion side. But anaerobic digestion still requires like biodegradable fraction of municipal solid waste. Okay, I don't think so. I will give opinion. Maybe it will be wrong if I will give it. So like I don't have expertise in anaerobic digestion process itself. It's just I use it for the heat balance, how much biomethane potential is available from the municipal solid waste and how much you are producing it. Like if you are asking me about how it will affect the process inside of the digester, then I don't have.
Or maybe I was maybe not thinking about on details of the process, but in general, like what are the challenges there, like on a more bigger perspective? So that was so. Maybe I can also discuss this. So what I think. So of course, one. If I speak on what are considered in Finland difficult at the moment is that, for example, wastewater treatment, the sludge from there, it's very wet, and but it contains nutrients, very valuable nutrients. But the challenge is that there is so much water in the digest state, that the liquid product, and then in Finland there are some areas that, for example, in the coastal area of Finland there are many of these big 80 biogas plants, and there's lots of cows and animals living there. But then the biggest need for fertilizers are in inner and eastern Finland. So then the challenge is that we have very wet fertilizer. It's not feasible to transport, and how to dry it sufficiently and enrich the nutrients to be so that we can transport them to central and eastern Finland. So I think this was what I was looking for. But do you know, is it same thing in Sweden also considered as an issue?
Okay, so I'm sorry, I misunderstood your question. If you're asking this, then I have quite opinions on this. In Sweden, there is one like certification system from the wastewater treatment plants. I forget the name, I put it in my thesis, where like it should be according to some standards. They cannot use it as a fertilizer directly. And if I'm remembering it correctly, in the last couple of years, only 30 to 35% of digestate from the sludge is utilized as fertilizer directly. Otherwise, it is not, it cannot be according to Swedish standards. But digestate from the biodegradable fraction of waste from the food or kitchen or restaurants waste, that was utilized directly in Sweden. I mean, approximately, I guess 99% was utilized as a fertilizer. But it has the same problem with the high amount of moisture high amount of liquid, and that's the same problem it occurred in my analysis also. Like when we wanted to dry the digestate, it requires so much amount of energy, and we are just doing the simple heat balance. Like if we want to model a dryer and how it will treat the waste, and because digestate contains so many inorganics also, it's not only organic, so it will be a difficult process also.
Yes, I agree. Yes. Okay. Okay. If we think about waste to energy technologies, just as a technology, so of course it's the not something that we would in a way would like to get rid of this this just burning to make more value. But if we think about it just as a technology, what is good in it, in your opinion? What are the best sides of waste to energy by just burning it? Do you have a comment on this?
Like if we just burn the waste, then
yes, I mean that, for example, in comparison with gasification or pyrolysis, what are the benefits? Why is it better?
okay, burning waste, it is easier to utilize heat from the flue gases in the form of steam, which can be utilized in a number of ways. For example, if you have nearby industries, you can provide the steam to them. You can produce electricity also, and like we see district heating. And if we don't see the case of Europe, if we go beyond Europe and go to my country or even India or China, like in my country, we still have a load blackouts. We still have electricity blackouts. So if in my area we have a waste plant where they are collecting waste and burning to produce electricity, all of us will be very happy. It will be because it's easier to process afterwards, but not with the gasification and pyrolysis. It requires quite a lot of downstream processing treatments, which are very delicate. And also, like in Sweden, they have the emission limits, so they are treating flue gases after economizer, after the boiler also. So this process is also state of the art. So it's not like something you cannot treat flue gases afterwards by cleaning all the emissions. You can clean all the emissions from the flue gases also. It will be expensive, it will be a burden on the plant, but still.
Yeah. Okay, this was very good. So I absolutely agree on that. And also, like if we think about technical readiness level, it's all very mature technology. And at the moment, I think, like if we think globally, we need matters like solutions that really can are mature and operate robustly. So in that sense, why waste to energy would be a good choice, but then we just would need to develop it further, I think. And also, as you said, gasification has lots of issues. It's very when you do the model, it's a very nice option, but in practice you face so many challenges. So somehow we need to think that how to combine these processes to make them more efficient and to make the change happen faster. So this is something that I'm very interested on this topic. So we have good, very robust technologies, but how to make them better for environment. For example, CO2 capture technologies, implementing them to them. But there are very many nice options to consider. Okay. Yeah, I think for the research questions that I haven't had a couple of questions on them, but your presentation was very clear, so I'm not going into details. Maybe I could ask that you had four research questions. So what do you think? What was the hardest to crack on these four? Where did you use most time to solve?
Yeah. Research question 1B and research question 4. Like if I wanted the research question 1B where I modeled the CHP plant in Epsilon professional with part load behavior, I wanted it from the very beginning of my research. And I did not know about this tool earlier. So I tried to model particle behavior on Aspen Plus. I tried MATLAB, but it was taking too much time. And in Aspen Plus, I need to like integrate MATLAB with Aspen. So then in the last couple of years, I got to know about the Epsilon Professional, and then I model the particle behavior. That was very difficult, but I wanted it from the very beginning to model it and use the results for the integration. And the fourth research question, like when I started modeling gasification pyrolysis, the same thing. I am getting a definite results. Okay, efficiency is 80%, but if it is 80%, how is change? I did the sensitivity analysis, but then I wanted to do this uncertainty analysis, and it took quite a lot of time to develop me the methodology and then do all the simulations and do the methodology. And I have to learn quite a new tools
Yes.
about this.
Yeah. Good. Also, just as a comment, the figure 2 on page 9, I think this is a very good presentation of on 3 perspectives how you papers answer. I really like this approach. I have never seen this similar, so this was I really enjoyed analyzing this. Then just maybe on page 11, there's maybe like the paper 5, you write that biochar is transferred to the pyrolysis process to enhance biomethane, while I think this pyrolysis process should be maybe AD process. It's yes, just note it. Yeah, okay, that's minor. Then on page 14, you have the technical readiness level analysis done. So in my opinion, maybe the you have well, atmospheric biomass gasification in the 4 to 5 TRL, but I think maybe generally that's okay. But for example, if we consider, for example, the power plant in Lahti, it has been running already 10 years. So but I think in most cases they still need a lot of development, especially for air gasification is quite far. But for example, steam gasification needs a lot of work still, and also you have municipal, well, this is maybe just a matter of opinion, but municipal waste incineration and AD processes in the border of deployment. In my opinion, I think they are a bit deeper in the matter technology, but this is just my opinion. Any comments on this?
Yes, like if on the text in the previous paragraph, like I have written that for heat and power production, gasification has high technology readiness level from 6 to 7, but for biofuel synthesis, it still is low.
Okay, good. I missed that. Okay, then it's correct. Good. Yes.
And the other comment, like this figure is actually taken from the International Renewable Energy Association report from 2012. And I have been communicating with them to modify this figure because they did not modify it. And most of their new reports, they are also saying they are still in this deployment and demonstration stages and all. So that's why I kept most of the things.
Okay, but this is good. Good. Then just as a comment, this was like in Finland at the moment, as a comparison with AD process, we are at the moment producing 1 terawatt-hours biogas annually, and our objective is to have 4 terawatt-hours by 2030 from biogas. And it was interesting to notice that in Sweden you have roughly 1.7 terawatt-hours currently. Do you know any future trends? How does Sweden see this biogas in the future?
I don't have the numbers properly, but maybe the utilization pattern will be different in future. Like currently 50% of the biogas is utilized as fertilizer, not fertilizer, as a vehicle fuel, and 50% in industrial applications. So maybe in future, more electrification of the vehicles, there will be more industrial use of the biogas, and maybe they will increase more, but I don't have idea.
Okay, so this is good. So I think that based on my understanding, the biggest value for biogas, we can get it from the vehicle as a vehicle fuel, like biogas car. And I think that this is a top, like a purpose, like we should maybe, we will need to have electric, we need to have, I think we will have electric cars, but I think we should also have biofueled cars as much as we can use them, because it's a very nice fuel. The process is very efficient, both economically and also environmental. It's quite good. There's circular economy aspects in making that, and so that's my opinion. And also I'm driving a car with biogas, and that's for consumer perspective. This is very nice fuel because it's almost half the price of gasoline if we compare on energy wise. So that's also something that I'm a bit surprised that it's not more common already, that sense. But that's just like a practical comment. Okay. Just to check, something is that you say that, of course, this is a common knowledge that gasification of waste offers higher electrical energy efficiency than waste incineration. So what is the main reason for this?
I'm afraid I don't have proper answer to this. The thing is, like, syngas cleans faster, a combust cleaner as compared to the combustion. But I actually did the simulations in Aspen Plus, where I was getting higher electrical efficiencies for gasification before writing it in my thesis, and it was getting it, but I don't have proper answer how, like, what are the reasons there.
Okay, so maybe there are many things, but when, for example, one thing is that like we can utilize these combined cycle concept, also like gas turbine plus Rankine cycle, and we can also, if we use pressurized systems, then we can decrease the volume and increase capacities. But just since you wrote it, I thought I asked yes, to check. Okay, good. Then on page 17, you talk about the pyrolysis of waste, and you only mention, if I'm correct, you mentioned the in a way the fast or flash pyrolysis, so very short residence time. Do you have an idea that what is the role of like a slow pyrolysis? Is it used also for this purpose, these kind of purposes, like waste pyrolysis or biomass pyrolysis?
I have seen very small literature about the waste pyrolysis already, but for biomass, slow pyrolysis has been in practice, and especially in developing countries, we have been using pyrolysis of the agricultural waste. Slow pyrolysis, we put it in a pit and just leave it there for days, and it becomes a hard black material, and we use it for cooking and heating purposes in our country. But slow pyrolysis, yes, for biomass, there are processes present. But for waste, I did not see much about the slow pyrolysis. But for biomass also, like for pyrolysis, it is mainly attractive for the bio oil thing. That's why I can only consider the fast pyrolysis in this cases, and we can make so much materials out of bio oil. With slow pyrolysis, we have mainly one material, biochar, and that has a limited applications as compared to, not limited, but that's not what I wanted in my thesis.
Yeah. Okay. Yes. And exactly. So it's a matter of, I think, what you want to produce. So for liquid fuels, which actually means that in the pyrolysis itself, it's volatiles that are condensed to liquids, and then the fraction of the char is much smaller in the fast pyrolysis. But if we want to maximize the char, for example, if we want to produce biochar, then the slow pyrolysis is better. So, but absolutely, you are correct on that. Then on page 21, you discussed the efficiency of gasification, and you give the efficiencies for CFPG, DFPG, and entrant flow gasification. So how are these efficiencies defined? What is the is it cold gas efficiency or?
No, these like for the first, I defined it as a production of biomethane. Like if you see, according to the paper from 2010, where researcher modeled the gasification for production of biomethane, so that was that efficiency. And mainly they are for biomethane efficiencies, all of them.
Okay.
For production of biomethane, like not the cold gas efficiency. Cold gas efficiency will be a bit higher than.
Okay, sorry. Maybe yeah. There's so much to read. Okay, good. That's good. Good. Then on the next page, you talk about the increase of biomethane production from AD by adding the biochar from pyrolysis, and you say that you can increase the production from 5 to 31%. So is it relative units or like a percent units?
Yes, like for example, if you are producing 100 megawatt of biogas, it can be 5% higher than 100 megawatt.
Okay, so this is really big change then.
Yes, and 5 to 31% is based on the literature review. And in this cases, I only used 5%. Like I did not, like there was no proper way of modeling it. So I took the like conservative assessment. Okay.
Oh yes, like in a lower limit to be safe. Yeah, good. Yeah, but that's very interesting way to do. Okay, that's not relevant anymore. Okay, this was now we are getting to your what you have been done. So the methodology, I think you start in the page 27. You said that your aim was to consider that all fractions of feedstock must aim to produce value-added products. So I think this is very good. So could you please comment on this? What was the thought behind this?
Yes. In previous drafts, it was written as all fractions of feedstock must aim to produce energy, and then no, waste should not be converted into energy. Value-added means it should be recycled if it's recyclable. It should be converted into other, if we can make biochemicals or biomaterials in an efficient way or according to the demand of the region, then it should be converted into those products. Like there should not be only 1 or 2 products that they are limited to. That is currently now only heat, power, and biomethane from anaerobic digestion. And in Germany also that biomethane is converted into heat and power after. So it should not be only confined into 2 products. So there are so many products that can be gathered from the all fractions of waste, not only energy, and it can be recycled and anything. So that was a thought behind this.
Yeah, and I think I like this a lot, that in a way you are developing a holistic solution for this municipal solid waste, and sometimes we see companies making solutions to an existing problem, but they develop a solution, but they might create 2 more problems by doing it. So this is why I liked that this approach that all that comes out should be like valorized in a way that is utilized. That's good. Yes, that was already answered. Okay, then you talk about this dual fed bubbling fluidized bed gasification, and then in comparison with circulating fluidized bed gasification and entrained fluid flow gasifier, there is no requirement for the air separation unit in the DFBG. So what is the reason for this?
The gasification requires heat, is a endothermic process, and oxygen or air is normally provided so that partial material should be combusted. So if the dual fluidized bed gasifier is not integrated on a standalone basis, it has two reactors. One reactor will take air, one reactor will take steam normally, as per Gobi gas plant in Gothenburg that is taking. So here the main thing is the second reactor is the existing boiler that is already taking air. So air is provided at that reactor, and in this gasifier only steam was provided. So that's why there was no air separation unit. And also when in this reactor, if there is only steam, there will be little chance of contamination of nitrogen. So that's why air separation unit was excluded.
Okay, good. Just like it's good to make these checks that very simple questions to make sure. Good. Yeah. So yes. So exactly. And yes. Let's go further. There are many processes here. I'm not going to in details of all of them because there's time. Let's see, where's the next question? Generally, you think that you mentioned here on page 50 the offsite integration of pyrolysis with AD and CHP plant. So you have a term soft linked to Aspen. What do you mean? What is this soft linked? What do you mean by this?
Okay, soft link is a term I got to know after 2 years of my research. Hard link is if I am simulating or I'm making a model in Python or MATLAB, and the results are directly transferred to Aspen Plus model without my any effort, without I am entering anything. Soft link is I run the model in Python, and I take the results from there, and I put it in Aspen Plus, and then
Manually.
Yes, so it's
okay. Yeah. That's so I got it correctly then. There's Okay, good. There would be a lot of questions for Aspen, but I think that's maybe I have later a couple of them, but let's not go into that detail. Then about the efficiencies, page 51, the equation 2. I think the equation 1 is quite obvious that you have the input is only the biomass for energy, but in the equation 2 you have also heat and power in the downstairs. So what is the idea here?
Okay, like equation 1 is utilized for CHP integration, and it was assumed that power will be provided from CHP plant, heat will be provided from CHP plant. So
yes.
Power.
Yeah.
But when anaerobic digestion was integrated with pyrolysis, it was different. Like there is no CHP plant coming, which is providing heat. Even if they provide heat, they have to. It's an external process. It's not the integrated one. And so that's why heat and power for anaerobic digestion and heat required for pyrolysis, heat required for the processes were used as input here. And for output, like in the pyrolysis process, there was some excess heat after the integration from the exothermic reaction of methanation that was extracted or that was recovered. That's why there is excess heat also.
Okay. Yeah, yeah. This is always when we have these kind of additional processes implemented. So it's a matter of where you have the control volume. In a way, and also when you have efficiency, downstairs or the divider is the what you are paying, and then upstairs is what you get. So maybe this is the easiest way to explain that. Here you are in a way what you are paying to put to get the product. You need to put extra heat and pay for the electricity to have what you want. So that was my thinking, that how I personally understand this, because usually it's, if you have think about just Rankine cycle, downstairs is the amount that energy comes from the fuel, and all is upstairs, it's then what is done with the fuel. So that's more simple to understand that. But of course, this is a logic when you draw the control volume in a certain way. This is also correctly put. Yeah, good. Good. Okay, this then page 54, that table 4. This is maybe, you just need to explain this to me that I understand. So, for example, scenario 1, it's the combined heat and power plant runs to fulfill heat and power demand for reference case, and only excess heat is transferred to gasification. And then this scenario 2 and 4, they in a way, these additional processes they need energy. So how was it the case for the CHP plant? Did you have constant fuel input for that all the time in all cases?
Yes, it was constant input. And if I remember, 16.3 kilogram per second of waste as per that was used. And it was modeled in Aspen Plus as steady state simulations. So I have to keep the same input. But then I run the simulations by integrating the model with Aspen simulation workbook, where for the whole year, for whole months, there was a different thing, and I was maintaining the heat as per each scenario, and I was able to run the.
Okay, yeah, but maybe I didn't quite put my questions correctly. So what I mean that when these additional processes need more energy, it's not so I mean that the capacity of the CHP plant was kept 100% all the time, and then this is an actual retrofit case. So we keep that constant. So if we need extra heat, so we can't burn more in the CHP. But that was my thinking, that I wasn't sure.
For the integrated process, yes, the waste input was different for each scenario. Like when you integrate gasifier or pyrolyzer, they also use waste, and there the input varies in different scenario and in different months, because if they are only able to utilize 5 megawatt of heat at one point, their input will be different. But in the next day or the next time, if they are able to use 7 or 8 megawatt, their input waste will be different. So waste was different for the gasifier and pyrolyzer integrated option.
Yes, but not for CHP plant, it was constant.
Yes, it was.
No, but this is good because then like in a actual retrofit case is that so the assumption is then that you are running the boiler with the maximum capacity. You can't double the capacity because it just won't operate. Yes. So then I got it correctly. So the energy was then, for example, for gasification, you had some of the waste was burned in the gasifier to produce the heat required, right?
Yeah.
Yeah. Okay. Then I got it. Good. Also, just as a comment, the figure 28 is, I think, quite good, and it took some time to hand calculate and check, but still I think I like this approach that you with the one look you see where are losses and like this kind of Sankey diagram type of. I really think this was good. Then just again, just I need to clarification for this page 56. These pictures. Now I don't remember what if it was written. Is this just one example year that you are studying here, or is it average?
Okay, this is the data from the year 2015 from the CHP plant.
Okay, 2015. Yeah. Okay, then yes.
2015, and then I had to modify the data. Like Aspen Plus was not able to operate when the plant has a 0 district heating. Something, so I had to modify it with average data manipulation thing, and
Okay.
that's
Okay.
why the CHP curve is not proper CHP curve, just like it should be. And but that was good also, because then we get the conservative assessments for the integration. Like we don't get so much biofuels in summer months. So
yeah, exactly. Yeah. Yeah, good. So then my question would be that, for example, well, for March, I think it was very warm March.
yes.
That was quite low, the amount. So that explains then, and so no. Okay. So, and also then the pictures in the page 57, it's clearly it was a very warm March that year, because there's lots of potential for additional production in March, for example, syngas for gasifiers, and so there was lots of excess energy. Okay, good. Okay, on page 58, you partially answered this in your presentation, but still I want to make sure that I got it correctly. So you write that simulations show that it is possible to extract steam at high pressure during off-peak hours without compromising the heat and power output. So so could you please explain still once more how can you see it from, for example, in the figure 31?
Okay, when you extract high pressure steam after the boiler, it is convenient option because steam has not undergone any process. Steam is produced, you can extract the heat, you can provide it to parallel process. So that's why it was like model was able to run smoothly without giving me any trouble. And we were able to maintain the district heating also first, and the only excess heat was extracted. But for low pressure steam, when there is another equipment there, turbine. So you have to extract from the turbine, and then you have three variables: steam coming, steam extracting inside the turbine, steam leaving for the district heating output that we should maintain. So it was hard to maintain the district heating. We could have like it all the curve was followed, but the district heating amount was lowered as compared to, because normally when you maintain the district heating in the reference CHP plant, they are also extracting live steam if the heating demand is very high. They
Yes.
are not producing electricity. But here I had to produce extra electricity just to only extract the heat from as a low pressure steam. So that's why we were able to follow while extracting the high pressure steam, but not when low pressure steam was extracted.
Okay, yes. I think that the figures are quite clear. But now it's not also, I'm sure that I understand, like 31 and 32, they are good. Okay, good. Then on page 68, you discuss the AD process and effect of adding biochar to enhance the process. But this is also there's a big impact. but also as I think at some point in the thesis you discussed that biochar could be also very useful in returning to the soil because the carbon in the soil it's dramatically decreasing, and this is non-renewable actually. So in a way this is it's a matter of what we should do, like have more biogas, or then to return the carbon to soil. So do you have a comment on this? You discussed it, I think, in the thesis, but would you like to comment on how do you see this dilemma?
Yes, like when I was writing the paper with my co-authors, and we had a discussion about the integration options, like that we excluded it in the final draft. Like instead of adding biochar into the anaerobic digester, we could have said that we will add this biochar as a soil absorbent there and just like check this option. But at that time, and still I'm not expertise on how it will affect, like what is the main methods and like phenomena that is behind this. So that's why we excluded it during that time. So
yeah, and also in the future work part of the work, you discuss this like the topics for future works, and then there you mentioned this hydrothermal carbonization, and that is something that I have been studying with my group, partly like I don't know the HDL processes, and there, for example, for wastewater treatment plant, after after AD process, we have the digestate, and if we would treat that in this hydrothermal carbonization, we would have a biochar that would contain carbon plus the nutrients, and that would be an excellent way to return that like a natural fertilizer plus carbon to nature. But this was nice to see that topic also in the future work. So good. Then on page 69, you have the figure 37. So could you please still shortly explain? This is very nice figure, but just to make sure that I understand. So for example, the standalone AD, that I understand well. But then the three remaining bars, could you explain what are those? So for example, first the incineration of green waste. What does that mean?
This is the lignocellulosic waste.
Okay.
I mentioned it with two terms: green waste in the paper and lignocellulosic waste as in the thesis. But in the figure, it's still green waste. I apologize for that. And like our initial, initially in the base case in Westeros, in the biogas plant, they are collecting the lignocellulosic waste and they are sending it to the incineration alongside refuse dried fuel. So I model the process and incinerate the lignocellulosic waste according to their elemental and proximate analysis.
Yes.
And I found, okay, we are getting the heat and power as a 67% efficiency. But then again, okay, we integrate the process with anaerobic digestion. We integrate pyrolysis of green or lignocellulosic waste with anaerobic digestion. And the next bar is showing that. But there you see the purple thing is the heat required for pyrolysis and heat required for the other processes. So in the next bar, I did not mention it in the presentation as it was taking too much time during practice, so I exclude that. There is offsite integration where pyrolysis was integrated with CHP plant.
Yeah.
And biochar was transferred to the anaerobic digestion, and all the heat for pyrolysis was taken from the CHP plant. So their purple chart reduced for only anaerobic digestion process, and we get the same amount of biomethane as we are getting in the third bar, but the efficiency is now higher.
Yes, yeah, exactly. Yeah. So then I got it correctly. So it's just like same amount
of bio.
but yes, exactly. But this is, I think, a very, very nice presentation of that result. Good. Then, okay. Then on on the next page, you talk about the drying, and you say that a lot of the heat in the digestate was needed for drying, roughly half. And then my question is that what kind of drying technology did you use for modeling? Was it just a simple simple heat exchanger, or maybe you could explain this a bit?
For in Aspen Plus, I use a simple heat balance method.
Okay.
Not that the design of dryer, but my colleague in paper 7, he modeled the actual dryer where the pedal U-shaped dryer was used for the drying. It was modeled in MATLAB, but that was not my work. That was his work. I utilized his result. But in for the first 3, when I was like case 5A, case 5B, and case 5C, it was modeled in Aspen Plus without any dimensions and without any drying technology. It was just, okay, we assume that we are able to dry this digestate and how much heat is required.
Okay. So okay, good. So in your but generally when we when we have a for example, and this was indirect drying, I think, like
Yes, indirect.
yeah. So then in the with the wet fuel, when you evaporate the water to steam, what happens that approximately the temperature of the steam is equal to the temperature of the solid part, and then when they leave that section of the dryer, we have a lot of steam that is it's in vapor. And for example, in pulp and paper plants, they are using this double effect. What's this drying system that they have? For example, 7 stages of drying, and what they are doing, they are actually utilizing the latent heat of the evaporated water in the next other stages. So when that then condenses, there's a lot of heat released to evaporate water from the flow. So it's in a way the counter current drying. It's very efficient, and in a way you can use the same heat multiple times to evaporate. So just as a maybe further idea, would be really interesting to see how much more efficient the drying could be made with this kind of technology, because it's very wet and there's a lot of energy needed, like as you said, half of the energy in the solid content. So this could be very interesting to see how much better it could be made with this kind of technology. So any comment on this?
Yes, like I remember when we were doing this paper for conference, and our co-authors, we were discussing this option. Can we recover the heat from the steam and somehow make the process feasible? But then we also decided it against it. We don't give some false hope to the research community with only simple modeling and simulation, because our model was not so complex. So like there was an option that we discussed, but then we discarded. So we said, okay, let's only show the negative results and then see how.
Okay, yeah. But this is also good that you are now, you know the lower limit, but it would be just for curiosity, like for interest to see how, because in of course this is in a pulp and paper plant, it's very robust technology there, but it's a really a liquid what we have there, the black liquor. But just for interest, it would be really interesting to see how much better efficiency could be obtained with that technology, because it's a big thing, how much energy is needed for drying.
And okay, I can add one other thing, like
Yes.
when the steam coming from the drying of sludge will also contain odor and other pollutants that can become alongside steam, so that can cause problems in the downstream processes. So that was also the issue that we discussed. So
Yes, yes. Also, like I recommend that take a look at how this is done in pulp and paper industry, because that you're absolutely correct that there are these different odorous gases coming from the evaporator plant, but they are taking care of these. They burn the gases to remove the like sulfurous species. And also they have a water treatment plant for the condensate. Of course, we have a very contaminated concentrate coming from the system. You're absolutely right, but still, this is a lot of amount of energy needed. So, an interesting research topic for postdoc period, maybe. Okay, good. Then. Okay, then the paper, page 73. At the last sentence, you say that the results also show that the simulations for the production of liquid biofuels are more sensitive to input parameters than those of gaseous methane. So, so of course, this was based on the Monte Carlo type of simulations you did. But what are the main reasons for this conclusion?
I think this is, like I mentioned in the paper also, this results are dependent on the methodology that I am using. Like I'm using Aspen Plus, and it treats production of biomethane through our Gibbs reactor efficiently as compared to production of methanol and dimethyl ether. The other main issue was lower conversion of syngas to methanol and dimethyl ether. I had to recycle it. So there were some issues with the convergence. So there were some outliers because of this. And with the production of gaseous, that was only one biofuel, biomethane. Syngas was converted to biomethane very efficiently, and there was no need of recycling it in the R-Gibbs reactor. So that was the main issue with this liquid biofuels.
Okay, yes. And also, like I think more actually on next page on this, I think your approach, this Monte Carlo type of simulations, I think this is very nice work, very impressive, and usually when we do sensitivity analysis, we just let Aspen to run through a certain range of for different parameters, and then we are happy with that. But I think how you did it here with the random numbers, it's quite impressive work. And also these, like the figure 41 and 42, they are really, I think, really brilliant way to study this. So, and also here, for example, figure 41, just 41. So I think you commented also already in the presentation, but then what are the main reasons that make bioethane the best option? And then Fischer-Tropsch fuels, they are on the lowest efficiency. So could you comment this? Why these differences? The main reasons for these differences?
Okay. I will only explain first on the simulation point of view, because these are the simulation results. These are not the actual.
Yes, yeah.
So when we simulate biomethane production, it is quite straightforward. You increase the hydrogen to carbon monoxide ratio to 3. You use the reactors and you do the kinetic simulations or just the equilibrium simulations, and you get the results. And normally high conversions are obtained for the production of methane to carbon monoxide and hydrogen. But with Fischer-Tropsch fuels, the main problem is the additional hydrogen that I write Fischer-Tropsch fuels, but they are actually finished drop-in biofuels at the end. So these are not
Yeah.
the intermediate Fischer-Tropsch fuels. So they required additional hydrogen, and process was complex. And the modeling approach I used, like it gives lower outputs. But even I have seen other modeling approaches, they are not giving higher outputs in the Fischer-Tropsch fuels. So that is the main reason. And biomethane is then, what's I say, it's not only a biofuel, it's a chemical also. It can be a precursor for a lot of chemicals. Like for example, if you don't make methanol, you can make methanol from methane also. You can make fertilizer from methane also. So that's why it's not only better in the efficiency point of view, but also it's like its uses are versatile.
Yes.
And they can also produce additional hydrogen that can be utilized with Fischer-Tropsch fuels. So
Yeah, I agree. But this is like and also you have the continuous distributions for this shown later. That I think that is a great value from the work, and like on page 43, these distributions in rate of return and net present value. I think these are very, very nice work. I really think so. Yeah. Okay. Then on page 77, in the middle, you say that DFPGs show the best technical and economical performance with minimal effects on the performance of the CHP plant. So could you comment on this, like in comparison with circulating fluid as bed gasification and entrained gasification? So what were the main reasons that made this the best option?
the first and foremost is the air separation unit that we discussed earlier. It requires electricity that was not integrated with dual fluid bed gasifier, and entrained flow gasifier. For entrained flow gasifier, pre-treatment was different. Like instead of drying, waste was torrefied, because entrained flow gasifier requires specific type of feed size, and so that's why. And it also requires extra heat instead of drying, like more heat than drying. And the output from the dual fluid bed gasifier only utilized steam. So there was less production of carbon dioxide as compared to circulating bed gasifier and entrained flow gasifier, where a part of waste has to burn alongside.
Yeah, so there's CO2 then.
So, and that's why high output was obtained, and effect was lower overall.
Yeah, but this is like in a way in my opinion, the cases that you have selected, they are quite good, and also give a lot of benefit for example for industry. And when we are thinking about the options, what should we do with municipal solid waste? I think this gives a very good theoretical support for these decisions. Then what was really interesting also to see in your work, that you had the electrolyzer used, studied also as an option to make hydrogen, and then there was the water gas shift reaction. These were competing in a way with each other. So could you comment on this? You said that that solid oxide electrolyzer cell, or it was better to use the water gas shift reactor instead of electrolyzer. So what made the electrolyzer option worse?
When I wanted to select this option, like I wanted the whole paper on the SOEC, electrolysis, but then I turned out I have very small time left, so let's only focus on the initial things. But then I use this option because it is gaining very much attention in the literature. And I've seen quite a lot of papers where they are producing hydrogen, that hydrogen for that can be utilized in further processes from electrolysis, not only for SOEC. And in the integration in the paper 1 and 2, I saw, okay, electricity prices are like vary from the CHP plant. And when I was talking with the CHP plant manager, they say like they plan the electricity and heat differently. So they have this main issue. I said, why not use the electricity from the CHP plant instead of the heating? Because heating is their main output. Heating is their main product.
Exactly.
So can we use the electricity and use this electrolysis to produce hydrogen and then utilize it with the production of drop-in biofuels? But then the main problem with electrolysis with SOEC specifically is this is not commercially mature technology for sure, but they have high efficiencies as compared to the other two options. But the electricity production is lower, and also electrolysis requires a very high amount of water also, and water is not cheap. So there are so many other issues also with electrolysis as compared to with water gas shift reactor. So that was I found in this article. But
Yep, but you are absolutely, yeah, I agree, and also there is, for example, well, in many countries, including Finland, there's a lot of discussion on going towards hydrogen economy, and idea is there to use renewable electricity, for example, from wind power in the case of Finland, or nuclear or power or hydropower to use big large capacity electrolyzers to make renewable hydrogen. But this is also I am studying this topic myself at the moment, using electrolysis as a part of this kind of a traditional waste to energy topic. So this is very interesting. I wish we would have time to digging deeper on this topic, but maybe time is going already fast. So okay. Okay, on page 79 in the conclusions, you say that the selling price of other liquid biofuels would need to increase to provide an economic advantage for power generation processes. How I see this, is it more that the fossil options should get more expensive? But like if, for example, oil is running out, so I think its price is currently going down because using less. But if the fossil fuels would get really expensive, then it becomes easier for the waste-based options. Do you agree on this?
yes, obviously, then it will be option. But then again, there will be these big companies. They will not let it happen, and so yes, I agree that all the prices has to increase further to make the biofuels more competent, especially in developed world, mainly where people can afford it at higher prices. So they can check it, but I agree. Like they have to increase. They have to increase to make it more competent.
Yeah, and yeah, exactly. Okay. Then in the page 80, you discuss this the economical performance using the net present value, NPV, and I was in a way bit surprised that you mentioned in some of the in the papers the levelized cost of different products. So so what were the main reasons that you didn't more broadly use the levelized cost power or electricity or methanol. Why didn't you choose this more broadly in your analysis?
I chose levelized cost in first paper only that I wrote. That was,
Yes.
I think, paper 4, anaerobic digestion integration. But then again, okay, you can call me lazy. Then with I followed the trend. All the economic analysis mainly follow this thing. Like the main difference in some of the papers are they gave the values in terms of minimum estimated selling price for the biofuel.
Yeah, but that, yeah, exactly. Yeah. So this is equal to levelized cost of.
So
Yes,
and then I follow this. Okay, I use the current prices and provide net present value and do the sensitivity. And then I have developed this methodology in Excel and MATLAB, and then I was following it for all the papers. So,
okay, but on the other hand, that was a good choice, because if you change the approach on the course of the work, you can't compare anymore. But also, in a way, I'm lazy too, because we are using the levelized cost of methanol, for example, and levelized cost of hydrogen. So now I would like to compare my numbers with yours, but it's not straightforward. So that's the main reason for this. So don't worry. Okay. Okay, this is a bigger question. So your work was more or less retrofit study. So you would have the CHP plant already there, and then you add different components. How do you see that for the future? Will it be like this for all cases, or will we see a total like greenfield study? I mean that we plan the whole system from scratch. Do you think we are going to see this kind of cases in the future also?
yes, there can be two options in future. For example, if you make a plant from scratch, you can manufacture two plants in parallel. One plant treats waste in CHP plants, and they have already retrofitting systems where they can extract and transfer the heat to the nearby processes. And another option is to make the gasification itself polygeneration process. Just like you said, with the cogeneration cycle, you can produce the syngas, you can compress it and provide electricity at higher efficiencies with Brayton and Rankine cycle both, and then you can also transfer the syngas if required for the production of biofuels. I think that can be more flexible instead of having this. And I will repeat the thing. The main idea with this thesis is that we wanted to show is that we can modify this existing systems in a manner that it will become so much efficient. So when you will design future systems, maybe they will not be the same that I am using it. They will little bit different, or they will be different altogether. But to give an idea, we can do a lot more that has already been implemented. So, and we can do a much more from the scratch also.
Yeah, so then we have much more freedoms to design the process optimal for the whole. So this would be an interesting, but of course your approach is very good, because we have a lot of existing facilities, also new ones, and they have still a long expected lifetime, and we need to change them for better total efficiency and to serve the polygeneration concept. So I think your approach is very good. Okay, I would have a lot of detailed questions on the papers, but I think I'm very happy for the discussion with you today, and I think I have learned a lot on this discussion, and definitely it's nice to see that we have a lot of common and a lot of common interest. So for the future, I think it would be really nice to have a chance to collaborate with your group in many topics. But I think the procedure is in your university so that I need to maybe say a few words before we let the panel discuss. So, like as an end note for myself, I think that the work is very impressive, and you have carried out very thorough analysis in your thesis. And as I said, it's really impressive amount of work what you have been able to do in just in a few years. Definitely, so there's more than sufficient number of publications of very high quality journals. And I think that in the defense, you did very good job, and you were able to defend your work very well. And there's no question that you wouldn't have done the work. So absolutely sure that you did the work yourself. So this is one purpose of the defense as well. And also you showed very especially the Monte Carlo type of sensitive analysis. I think that's really innovative, and I can just imagine how difficult that was to to make that happen in a computer. So congratulations for this. And this was all for my part. I think it's now time to let the panel to have their word. So thank you for this discussion. I really enjoyed this part. Thank you.
Thank you very much, Mika, for an interesting discussion. So we let the examining committee ask their questions now. So should we start with Cecilia?
Okay, thank you very much. This has been interesting to listen to, and I agree that this is a very thesis rich in content. It's not just volume, but also content inside. So it's been very interesting to hear and read, and many things, of course, that could be discussed from here. But I'd like to start from the end with the last paper. You did this large analysis of uncertainties and sensitivities of important parameters. And this is closely related to the processes that you studied before. I was wondering then, from the results there, if you could mention some questions and perhaps even answers to those questions related to the previous papers that arise from these results. Is there something you would have investigated, some other scenario, for example, in some of the previous papers?
Yes, like if I understand it correctly, you are saying that can I link the results with my previous papers? And answer is like yes, because in the previous paper, most of the answers are definitive. I am giving, okay, from the dual bed gasifier, you can get this megawatt of biomethane or this megawatt of methanol or dimethyl ether. But how uncertain I am, like if I give these values to any other stakeholder other than researcher, if I want to give to any policymaker or any politician, they will surely ask me how certain are you? Like your process will give 50% or 60% efficiency. Are you sure? So last paper is there to make sure to question your own judgments, like or to provide the biases in the results. How we like all the researchers, when they are doing modeling and simulations, they have their own judgments of the assumptions or some input parameters. So how sensitive they are, like how certain they are with all the results. So that's I wanted to show with all the papers. Okay, don't take the values as a definitive in all the results that I presented in the last in the first 7 papers. Also see what are the assumptions I am using, and if you are reading the similar process in another paper, just see what are the assumptions or economic parameters or the inputs they are using. So that was my idea in the last paper. So,
and what is there any warning, anything you find that this is very important and this could actually question the conclusions made in a previous paper?
Yes, like the waste composition is the one thing. Like I chose the waste composition as average value that was taken from the CHP plant. But if we change the waste composition a lot, like I am using a very low heating value waste, 12 megajoules per kilogram. So if you're using a high heating value waste, results may become very much better. Or if you, and also the ash content in my analysis was 40%. So it will also affect the mass balance in the further processing. So if there is a less ash or more ash in the waste, in the like in my previous in the waste, so it will affect the results accordingly. And as for the economic performance, I chose the capital investment for the equipments from the previous literature. But as I mentioned, also like the value varies with so much literature. Like in some of the paper, if they say dimethyl ether production plant has a capital investment of 500 euros per megawatt hour, in another paper, it has a different value. And we have to rely on those values from the literature. Like I have to decide which literature I'm using for the economic analysis, which will also affect my decision on the previous paper. So if another person is trying to upgrade my processes and they will choose some different economic parameters, maybe they will come up with different economic results. And then one of the most important economic indicator that I found was a discount rate that was utilized for the determination of net present value. Like I chose 7% of discount rate in my thesis, which is on a lower side still. But if you change the discount rate in further economic analysis, it will affect largely the net present value. Even the smaller change will affect quite, like smaller change in discount rate can make the process feasible or non-feasible economically.
Okay. Yeah, I also find this with the waste quality interesting and how that will affect. And to a large extent, the waste quality is external, depends on what people will throw away. But there are also options for the plants to control this or through upstream work. I mean, first they can have quality requirements for what they accept. But I realize there's also options here, for example, with the anaerobic digestion, where you have the it's mainly food waste going to anaerobic digestion, and then you add the pyrolysis with lignocellulosic waste, which is largely garden waste, right? And I was just curious, could there be a possibility here for optimizing by moving waste between these fractions? For example, by changing these instructions to households, what to actually send to anaerobic digestion or to the other pyrolysis.
Yes.
What do you think there?
Like when I visited the anaerobic digestion plant to get the data, one of the main problem they are getting is people are still throwing waste in plastic bags, not in the bags that they are providing it. And they said, like for example, for the anaerobic digestion, eggshells are not required, but people are putting it. So it's very hard for some people to change habits. And if I say it in my home also, when I throw the garbage in the waste bins, I see so many plastics there in the food bin. So yes, we can change the behavior of people, and it should be changed. It should be like more communication on both sides, that this is not required in the processes. It will affect our processes for the production of biomethane, that we are using it as a community. But then it has to be communicated on both sides. But I agree, yes, like waste quality can be changed by changing our own behaviors and how we are using the waste and how we are throwing it and collecting it in our homes.
Yeah. Okay. Then I wonder if you could tell me and explain a little bit about the time steps and the time dynamics. Also in this 8th paper, you're saying you're using a time step of 1 minute in the change of the quality of waste. Why did you choose that, and how does that affect the outcomes of the modeling?
That was a judgment on my own side. Like I could have say the waste composition is changing every hour, every day, or even every week, but I chose it so I want to make the results in a wider range if I'm changing the waste quality at every minute. Although maybe it may not be the case, like I wrote in the discussion, for example, if a single batch of waste is coming from one side, maybe it will have similar properties and that batch will used for a whole day, and next batch will come next day. So it will have a different range of properties. But that was totally my own decision. I wanted a wide range of simulations so that I get more data to have a better understanding.
Okay, so it's mainly to get a large number of data. There's not a dynamic in the models that is affected by the choice of time step, or?
It will be get affected, like I will be able to finish the simulations in smaller time if I chose the smaller time step. Like this took a lot of time for the whole simulation to run, sometimes 1 or 2 days. But if I change the time step, and if I reduce the time step or to 1 minute or 1 day, then the time required for the simulations to perform will be less.
Yeah, but if you'd said the, oh well, if you had 10 minutes between the change of the waste, but run it for a total of 10 times longer, would that give you the same or a different result?
It will give me different results, I guess, because the time step is changed, so random numbers will be different there. Because here, for example, for 1 minute time step, total of 480,000 random numbers were generated for the waste input characteristics. So if I change the time step, those will be changed, and maybe the whole probability distribution will be similar, or maybe not. But I don't have any idea like how it will change if I change the time step or include other variables in this.
Okay. I think those were my questions. I've been trying to come up with something to link to what, I mean, the final thing in your presentation there with the cooking fuel, because I'm had the opportunity in the past few years to work myself with microgasification cook stoves in Kenya. But I don't know how to link this to your thesis, but maybe you have thought more about how your expertise could actually be used for those important questions of billions of people cooking with very poor technology and unhealthy.
When I wanted to finish the presentation, I don't have any idea how to finish my presentation. So then I came up with this thing. And like cooking is the most important part in our lives. Like we live for food. Food is the most important thing. And I have been living almost all of my life in my village, where I see like women where they are cooking outside of their outside with these kind of stoves, and they have to like collect the waste and burn, and not only the waste, like wood and other agriculture residues and all for the cooking thing. And at that time, I did not know about the hazardous stuff. That I got to know only when I moved here and I was researching for some other things and I read some books, then I got to know about this thing. And that is the main issue. Like in the people in developing countries, they don't know about how hazardous it is for their effects and how it is affecting in their health in future, especially for the women and kids. Like I don't have any expertise. I will say this again and again, like it's my general opinion and kind of a borrowed opinion that I have been reading here. And my other opinion is on this, it should be, those communities should be included when we are designing the equipment for them. Like I can make a very highly efficient stove for people who are living in a remote area in Africa or even in Pakistan or even in India, but then maybe it will not be efficient for them also. Like I have been reading a book on this. Book name is Invisible Woman, where the author gave an example of this. Like they made a very highly efficient stove, and they said like after 1 or 2 months, women stopped cooking on the efficient stoves. And they like researched again and they found the reason, like it was taking too much time for the fuel preparation. It was taking too much time for the cooking. And so, and then they understand, okay, we have to include those community also. We cannot blame them. Okay, we make a very efficient thing for you and you are not using it. So that is again the borrowed opinion, because I read the book. Like those communities should be included, how they want their stoves or how they want their cooking with efficient fuels. And the other thing is I found methane as a good cooking fuel that can be produced from biomass, and that can be transferred, and that can also be produced from anaerobic digestion. And in villages and remote areas, we have so much animal dung also instead of food waste, but we can produce this methane and that can be utilized as a cooking fuel. So, but the short answer is those communities should be included in the research, not only us, we are doing it here in developed countries.
Yeah, I'm glad that you came with that, because I fully agree there. And there's a lot about how you use the stove, and efficiency is not just about the energy efficiency, it's also about the time people have for cooking and for everything else in the household. So, yes, thank you.
Thank you, Cecilia. Jukka, do you have any questions?
I'm sorry, was it me?
Yes.
Yeah, okay, thank you. Thank you for this very thorough presentation. And I agree with Mika that you have made really a massive amount of work here. So, and I would say that it's enough for a PhD thesis in many ways. So I would highlight this issue, your research question number 4, this uncertainty. And with that, we could go in the beginning of your thesis, in the page 16 and 17, you talk about you refer to the present gasification plants. So I have heard that Cushing plant went into bankrupt. So do you know the reason for that? Why did it continue?
And I only know that they are not operating at the moment, but I don't know the reason about this.
Yeah, because maybe it's not that cost efficient, and they didn't continue to support the financial support from the government. That was not continued. So, and they lost this kind of support money. So maybe that's the reason why they are not continuing. So they had their demonstration period and then they stopped. But there are other plants like that in Austria and also in Kobe gas. So, but how about this Kobe gas plant? So why didn't it continue after this demonstration period? It has the same principle of technology as the Cushing.
Yes, I attended one course a couple of years ago in Luleå and Umeå University, there where they discuss about this Gobi gas, and they also run out of the funds about the thing, like they have the financial issues. Maybe they will operate it. They are trying to gather new funds. I don't know if they gather it now or not, but it was not operating at that time because of the funds unavailability. And also there is integrated plant for the bioliquor in Piteå in Sweden, where they are producing methanol and dimethyl ether, and they also demonstrated it. Luleå University demonstrated it. A car run on methanol, but that plant is also not in operation because of the funds, according to the lecturer during that time. So I think economic is one of the major issues.
Yeah. Yeah, I agree. The price of the operation cost and the price of the fuel that they get or the product, it's not economical enough to make it a good business. Yet those plants have not been multiplied yet. So it was the aim was to multiply the plants, to have different plants in different parts of Sweden and maybe in the other countries as well. So that has not happened. Yeah, you mentioned the Piteå plant, so I was also referring to that. So do you know about this? Actually, I don't know about this Lahti gasification plant. So what is the present situation? I heard they had a lot of operational problems and a lot of shutdowns. So have they been able to overcome those? I don't know the recent situation.
I did not know about this. Like I tried searching when I was writing the literature review for thesis, but I did not find much information, only the papers from the last 8 or 9 years.
Yeah, okay.
I did not find it, the recent thing, but they are doing it.
Yeah, I think that they are now building or using other types of technology for waste bioenergy use instead of gasification. I think one reason is the operation risk. And they had problems with gas filtration and blocking of the filters, and they had to shut down because they have to filter the gas after the syngas before entering the combustion chamber, and that was the problem. They were generating some blockages there. So, but maybe they don't talk in publicly much about the problems. But it was not a big success either. So, but anyway, it has been running and operating very large-scale gasification units 2 times 80 megawatts. So my summary about considering waste as a fuel for these gasification plants. So in general, the problem with gasification plants is the high capital cost. So and the high risk for investing in the plant and also the operational challenges as we discussed. And also one issue is the gas cleaning. And in your thesis, you should propose some methods of gas cleaning like tar cracking and then water gas shift and then some scrubbing. But I would say that could be a bit optimistic, having some experience about gasification for 30 years, I would say. Can you comment on that? Gas cleaning.
Yes, like in my simulations, I assumed we are able to reform tar, but like we all know in actual, it will not be the case to remove tar very easily. Like I have seen PhDs based only on the tar reforming thing or tar cracking thing, where they are developing different catalysts on this. So it's still not properly established technology. And also with the syngas cleaning, like I assume that I am able to remove all the contaminants, but I know it will not be so easy and it will be difficult when we will want to implement it commercially.
Especially if you have any kind of catalytic processes downstream. So if you have sulfides or chlorines in the gas, they will absorb, there will be the chemical reactions to chloride, inorganic chlorine compounds, and they will poison the catalyst, and that can be a big problem as well. So, and alkalines and heavy metals they should be removed and I think the requirement for the catalyst manufacturers was like in the ppb, parts per billion level, should be the levels of heavy metals. So can you comment on that? So.
I agree with you on this. Like I was optimistic in my simulations that we are able to remove all the contaminants, but in actual it's not. And these are the actual difficulties and actual constraints when we will apply this process, even on the pilot or demonstration scale.
Yeah, I think that considering in the simulations, you might need to add some couple of more cleaning steps. And that could be interesting to see how the economics and the performance would change if you have these kind of zinc guards or rectisol processes for removing the rest of the sulfur and so on. But if you have seen the reports from VTT, they are considering those in case of fissure drops.
Okay.
Yeah. And then about considering the operational issues, so these waste type of fuels, they contain these inorganic elements like potassium, sodium, calcium, aluminium, and they might cause agglomeration. So are you aware of that?
Yes, they can even if they're present in biomass, feedstock, or wood, they can agglomerate there, and waste is not purer than wood or biomass, so it will be higher issues in waste. So I read about it, but then I did not touch it in the modeling and simulations. I assumed it will not be a problem in my simulations.
Yeah, that can be a problem. Optimistic assumptions. And in gasification, the atmosphere is different because of the reducing conditions, and in combustion, and even in combustion, it is a challenge. So, especially with certain types of very like biomasses or waste type of biomasses, agglomeration or sintering. So if you are using fluid aspects, your bed material could sinter and form some bigger blocks, and you will cause defluidization. But how can you predict that with some simulations? That is a challenge. So
I think we need to do the detailed CFD simulations for this.
Yeah.
That I am not expert in. So, but
Yeah.
with the S1 plus simulations, these are mainly mass and balance and heat.
Yeah, that's right. Yeah, you need to have some simplifications, that for certain, to be able to estimate the whole process. That's for certain. Yeah, okay. Then about the fuels that you produce, like for example, the fissure drops liquids. So what do you consider as a fuel? Or so is it a fuel that goes into can be fueled with cars, like a petrol or gasoline type of, or because it requires a lot of intermediate step for the refining and distillation of different fractions of hydrocarbons in the raw oil.
Yes, like I write the Fischer-Tropsch fuels just to distinguish it that it is produced from gasification, but I consider the final product after hydrocracking and hydrotreatment and after all the distillation. So it was final gasoline and diesel mainly.
Yeah. Okay. So there was some post-processing after the Fischer-Tropsch reactor itself. So. But even then, you might need some distillation to separate, like diesel fractions and then gasoline fractions.
Yes, and like that was also simplified. Okay. Like instead of modeling of distillation, I said, okay, let's separate it.
Oh, okay, I might have some more detailed questions, but maybe one at this point because of the time limitation, I think so. So about this, considering you have these correlations about gasification and pyrolysis products in paper 1, tables 4 and 3 and 4. So where are they coming from? So are they like general correlations, or are they specific for certain type of waste or biomass? Or can they be applied in more general manner?
You are talking about correlation in the last paper that I...
Paper number 1, tables 1 and 2, 3 and 4.
These correlations, are you talking about the devolatilization of waste biomass? That has been taken from the previous literature that developed that have the pilot plant where they developed these correlations after running their pilot plant experimentally.
Yeah, what kind of waste biomass was that, if you remember?
That I don't. They are using. They made the correlations for different types of feed. So it was not only biomass.
Okay.
So they did the data analysis for different types of feed. They were ranging from agricultural to waste to biomass. So that's why I used them.
Okay, so that's the reason. So it's like a more general. So these parameters have been fitted in more than one fuel type, maybe.
Yes.
Several types of feedstocks. And the same thing with the table 4, where you have the gasification reactions. So they look like more general.
Yes, but mostly I have been taking those reaction kinetics from the papers. They were use waste as a feed, not as biomass as a feed. So
yeah,
it was most of the reactions were from those papers.
Okay, those were, I think, the most immediate points that I had. But maybe I'll let the other persons also to discuss. Maybe I can add something more later if there's time. Thank you.
Thank you, Jukka. Elizabeth?
Okay. First, I want to start with congratulating you on this very comprehensive work, and thank you for a very nice presentation and a discussion with both opponents and the other members of the committee. And then I would also like to take the chance to congratulate the MDH and the supervisors on picking you up when you were reaching out, as apparently we had no job opportunities at that time at LTU. So that's nice for your colleagues and MDH. And then I see that many of the questions that I had have already been addressed in the discussions, but I have some still. So we had quite some discussions on the technology aspects. So I would like to go a little bit into the methodology and in particular the price, the economic evaluations. So I want to start with a question about the pricing of products, because when I was looking at the different papers, and I see that there's the market value you have assumed for the different biofuels that you are producing. Since you're using this NPV, the method you're using, you have to have an assumption about the market value of the product.
Yes.
And you have, if I see correctly, you have for methanol, you have some 64 euro per megawatt hour from using Methanex as the source. For DME, you have 106, and there is Alibaba as the source.
Yes.
And then you have for methane, you had 100, I recalculated to 127 euros, and that's coming from another scientific publication by Christina Holmgren et al. And then for the FT fuels, I found a source a bit strange, and maybe it's an error in the reference list, because that was 180 euros per megawatt hour coming from a source, a web page, swedentips.se. So maybe there is an error in the reference list. I don't know. I couldn't find that web page.
There should be an error.
It's possible, but anyway, the results are quite, I mean, the range from 64 to 180 euros per megawatt hour in the value is quite like large. So can you explain a bit how you were reasoning about the intended markets for those different fuels and how they kind of like differ from each other?
Like when I was taking the value for methanol, I did not find a very I was trying to find if any country or anywhere where they are selling methanol at some price. And one way was to find, instead of finding net present value, find the minimum selling price to break even or give some rate of return. But then again, it was the discontinuity for all the procedures that I've been following in all my papers. And that's why that was the only source I took, and I wanted to I wanted to make methanol more feasible. But it was not able to do, and that was the only source I found for the price, and that's why I chose this as an option. Like otherwise, if I use some assumptions that at that time I was a kind of a very early researcher. I'm still very early, but I was a beginning, and I had to argue with the reviewers how I chose this price. If I can take 100 euros per megawatt hour or 120, but then some reference should be demanded. And that's what I'm saying. Like, for example, if I do the same paper for drop-in biofuels now, the prices are lower to 140 to 150. So now they will not show much economic benefits as compared to they were shown when I wrote the paper last year. So like my idea was to just take whatever we are present in, what are presented in literature. Same with dimethyl ether. Like in like Alibaba, there were so many options where they are making dimethyl ether very expensive. So I found where they are selling trucks, whole tankers of dimethyl ether with 1,000 liters, and that's where I took this price, mass price. Although I found some like 5 euros per liter also price for dimethyl ether.
But is that dimethyl ether intended for transport fuel use, or is it for chemical use as a chemical grade?
It was mainly for chemical. Like, why would someone buy fuel from Alibaba?
So no, because I mean, another way to approach this could have been to say that the selling price or the value would be like comparable to either the fossil counterpart or other biofuels, for example. So it also makes it a little bit difficult to compare the results. And that brings me to the next question, which is the figure you have on page 63 in the kappa, where I hope I understand correctly, you have combined the results from paper 1 and paper 2.
Yes, yes.
Yes, good. And there, I mean, you also say that I heard your reasoning about why you were choosing to evaluate the net present value instead of the levelized cost of energy or like a minimum fuel selling price. And so that was one of my questions, but that has already been handled in the discussion. But you're also like comparing the magnitude of the NPV. But have those figures been harmonized in some way between the papers?
No.
Or is the results directly from the papers in the values, or have you harmonized the kind of like input data and assumptions?
No, like they are separately. I wanted to do it, but then there would be so much difference between the papers and the thesis that I don't want to make it more complex. But then again, that's why I showed the capital cost. Like methanol and dimethyl ether have higher capital expenses also for the production. And like this is also an indicator. Like even though if the prices will become higher and they show higher net present value, but then there are other things also. But like I did not do any harmonizing. I just changed the payback period. Like in the papers, it is simple payback period, but on thesis is discounted payback period.
Okay.
Like so.
Yeah, because I noticed that you had different discount rates and different prices for the different fuels. So it makes the kind of like exact comparison might be a bit.
And
I mean, it might not be fair to some of the fuels how that comparison if it's done straight. But now I hear what you're saying. I also noticed in this you're actually showing the specific capital cost and specific net present values per megawatt hour, but you have in the equation, and that's the same in the papers. But in the equations you have actually the total net present value and capital costs. But here is the
like because in different scenarios we have different production of fuels, so it is also not fair to present only net present value in terms of million euros. So I divide the production by this megawatt hour, and so that's why. And the other thing I want to show, like for methanol and dimethyl ether, I chose a very low discount rate, 5.
Yes.
So that was also the thing. So, but still, it was not becoming feasible. So what else I can do?
Yeah, I'm glad you're commenting and saying that it is very low, because it really like depends on which kind of perspective you're taking. So that's good that you are commenting on the magnitude of that. And then I want to ask, because I'm going back now to the kind of overall aim of the thesis, which you have presented, and saying that this is to, let me see now how exactly to increase the product portfolio of existing waste managed technologies by integration of those thermochemical technologies and concepts. And who is the intended recipient of these results? Who will use them?
Apart from future researchers, hopefully, I intended industries, like they should think or about to approach their products. Like not every region in Stockholm requires electricity from waste in future. There will be like renewable options. District heating demand will also get affected if the efficiency of buildings will improve. There will be high insulation, new buildings, they will have other systems. So we are talking about heat pumps also. So there will be, in future, there will be a change in the infrastructure of all these things. And that was the aim, like even though methanol and dimethyl ether are not economic feasible, but maybe in some of the countries where people are more educated, people are more willing to try the biofuels, people are willing to pay higher to use these biofuels in their cars or in their vehicles to get the higher environmental benefits. But in some regions where they only need the biomethane, that can be the possibility. But if some like if some countries' whole economy is based on gasoline and diesel, where fish oil biofuels can be utilized. So that was the idea. So these biofuels, even though they are different in efficiency, difference in economic results, but different regions will require different demand and they will have different behaviors of utilizing it. So we have to see every option differently in different regions.
So researchers and the waste management industry are the main recipients, if that's what you mean.
And also the waste production.
Yeah, exactly. But I wonder how they will, I mean, for the researchers, I can understand. Researchers are good at reading research, hopefully. But how will the industry use this? Because this book, I mean, it's a great book, but it's also kind of like, do you have some kind of like popular version of this? Like, how do you transfer the message to the industry?
Okay, the industry. That's why I put the last paper, uncertainty analysis. Like it's
But
the most.
will they understand this? Because it's a quite complex problem. I mean, how will you give the message to them that this is good things, and how can do they have to read the book?
Okay, that is the difficult thing to answer, to be honest. I hope they read, but I know they will not read. I know no one will read after this. So, and that's why, okay, I can give you my opinion on this, not on the book, but we need to write the science in a simpler manner. The way we are writing the research papers are not the way we want to communicate science to community. But I have to follow the trend. For example, with this first chapter here, I wanted it, my supervisor wanted to remove it, but I did not. I said I will not follow the trend where I was putting the rationale for waste integrated biorefineries. So, and like in the thesis is we have to present the most innovative work in our thesis, but then we have to follow the basics. So we cannot do so much in writing. We have to follow introduction, research methods.
Obviously, yeah.
Results.
But maybe you should consider doing some kind of popular science piece on this, like a really kind of summary for policymakers, summary for industry, or something that is much more easy, where you will not go into the details. Don't even go to the cases and the scenarios and everything. Just like give some kind of nice and cohesive recommendations. I think that could be valuable.
Yes, actually, in like USA, there is a competition among the PhDs where they have to present their PhDs in 1 minute video. So maybe in Sweden, all the universities can organize this competition, and
that is nice. So my final question, since I'm the last out in the committee, I would also like to ask you, what are your plans now after defending this thesis, or have you already a position?
No, I'm still looking for, but I want to continue in research, and some of the future works that I'm already interested in, that I have been mentioned, because I'm interested in those future works, and I'm still looking. Hopefully.
Okay. So you're open for, if people come with the job offers, you are open for them?
Yes, I'm.
Thank you. That's all for me.
Thank you, Elizabeth. So now I open up for questions from the audience. The reserve, yes.
I also have another question.
Okay, Xing, do you have any question?
I only have one, maybe. Stella, you can go first. Or...
Yes, I wanted to ask about efficiency. You have these indicators that you discussed also with the opponent on page 51. And I'd like to ask about the first equation there, where you have heat plus power plus biofuel, and then divided by the biomass input. Just adding biofuel, heat, and power by the energy content, and comparing that then with different biofuels and different balances here. Is this a fair comparison? And why so? And if there are limitations, what could be done about it?
The first thing is this is integrated process. So all the boundary condition is that waste is input in the integrated system. All the required heat, all the required electricity is produced in the whole boundary system, and the excess biofuel that we are producing. So that's why it's a very simple equation. Like if I use only standalone gasification, then it will be, or change the boundary conditions, then maybe equation will become more complex. And like the same equation is used for all the biofuels. So I guess it is a fair for all the biofuels when we are comparing it on this basis. But there can be other indicators. Like I mentioned flexibility for only like research question 1, but flexibility is not a small issue. Like gasifiers are operating at part load in my systems, and I did not model the part load behavior in this thesis. But in future, I can model the part load behavior of gasification, and then the cold gas efficiency of gasifier will also change, which will also affect the efficiency of the whole system. But I'm considering the whole system, so that's why this equation is used for the whole efficiency, and I think that was fine for this analysis.
Yeah, but I think you have some underlying assumptions here about waste and power. I'm sorry, heat and power, because heat in general is not seen as valuable an energy product as power and biofuels, right? And how are you dealing with this in your comparisons?
Yes, like for example, if we change the region from Sweden to, let's say, for example, a warmer climate where there is no district heating production, then we have to remove the heat. Their heat is not valuable to the community. Then we have to only consider the electricity and power, and efficiency will be very lower. Like here, the efficiencies are higher just because of district heating. Like methanol and dimethyl ether show 68 or 66% efficiency just because of district heating was recovered. If we remove the district heating from the equation, the efficiencies will go down to 50% because of lower electrical and lower biofuel production efficiencies. So it was taken for Swedish context. So that's why heat was considered as valuable product here. Like here, heat is district heating. Maybe it's not the heat for the industry, it's just the district heating heat. So in another country or in other assumptions, it will be different, and it will affect the results differently. But then again, the efficiency for the biofuels production will be the similar. Like they will affect just because we are not using district heating as an option. I hope I.
Okay, thank you.
Okay, then I have a last, maybe one last question. Thanks again for the very fruitful work. I have a question about future work. Would it be possible for you to include other uncertainties, for instance, the demand from the buildings or mobilities? Because I found this from your cover, you include that, like the building demand and also mobilities in that. I don't know whether it is possible later on for you to include this evaluation or assessment into the integrated waste-to energy process.
Yes, it should be possible, but then I need to gain expertise, or I need to find a PhD student to work on my behalf. on this, but yes, it is possible. Like our another group which is working, we're working extensively with the district heating demand, and there is another group who is working with the heat pumps. So they are trying to relate with the flexibility of the system. And so,
and I mean, to your more like knowledge so far, do you foresee any influence to your simulation if we include this demand variation?
yes, like I only take the data from the CHP plant for the last year, like in 2015 and 2017. But when, for example, if we integrate the CHP plant and we have to plan the production of the gasification through integration, then we need to rely on the data from the buildings, how much district heating they are consuming, or next day, okay, next day, this is the forecast of weather, this is the forecast for district heating demand. So we can plan the production from the gasification or pyrolysis integration system. So it should, like I am using the historical data from CHP plant, but if this process will be implemented, then and then CHP plant operators has to rely on the data coming from the buildings. So before that, we researchers has to design some methodology how they can link those research areas together.
Oh, right, thank you.
I have a short.
Yeah, any further question from the committee?
Yes, I have a short question. That can you comment about Aspen as a simulation tool? So, but good features and the limitations. I think you mentioned that you have used this kind of Phoenix pre-processing or post-processing calculations to add in simulations.
Yes. Aspen Plus has limitations when they are using non-conventional component, for example, biomass and waste. We have to rely on the elemental composition, and sometimes and which can make error, not error, maybe like deviation in the results. And the other limitations is that it's very good for the steady state simulations, but for dynamic, you need all the conventional components. Like I wasted 3-4 months to just make a dynamic simulations for gasifier, and I failed. And that's why I use Epsilon Professional, another flowsheet based software, where it was possible to do the part load simulations. That was also not possible in Aspen Plus. And Aspen Plus has a module called turbine, but it do not have extraction point, which is a limitation. Like we need to extract heat from the turbine, which was not easy to model. And then with the pyrolysis, I found it very easy when I was using the programming language, Python or MATLAB. That's why I use those language. I take the results and go back to the Aspen Plus and just use the yield reactor. But I have seen some articles where they are using everything in the Aspen Plus, but then there will be some convergence issues. But then again, when we are using the downstream processing, for example, when we are only dealing with carbon monoxide and hydrogen as a syngas, then it becomes very efficient, because then we are dealing with conventional components, and also with gasoline and diesel. It is widely used in petrochemical industries and petroleum industries for the analysis. But with this biomass and waste non-conventional components, it needs to be upgraded in future.
Yes. Yeah, sorry, I meant Python, not Phoenix. You had used Python coding. So the reason why I'm asking this, that if you read the papers, they just say that this was simulated by Aspen Plus, period. So there's no criticism about the simulation method itself in the papers, so, which is missing many times. Okay, thank you.
Okay, thank you. Any more questions from Elizabeth or Cecilia? Thank you very much. So then we open up for questions from the audience here at the stage and also online. Any questions? No questions? Okay, in that case, I thank you all for this part and close this part of the open defense. So now the committee, you and the opponent, you should log into the that other Zoom room I sent you the link to, And I will meet up with you there, and also Professor Young.
Can we take 5 minutes?
Yes, of course.
Okay.
I will move to another room. So
Oh, okay. Perfect. See you there soon.
Yeah. Maybe I find something.
Okay, so
And we will come back to this both Zoom room and here when we have had the meeting.